collaboration with CSPP Geo and LEO on level 2 product software. Mikael.
All right, thank you for having me. I'm Mike Butler with ASSISTT, as you mentioned, which is led by Priyanka Roy, who is also with us at this meeting. And we support NOAA NESDIS on level 2 product software with CSPP, Geo, and LEO. And in this talk, I'll kind of just give an overview of what we've been working on and some future directions. So I'll start with kind of an overview of our role in the research to operations process and where the deliveries to CSPP come in, starting with CSPP Geo. I'll cover some recent deliveries we've made to CSPP Geo, talk about some of the changes coming in how we deliver algorithms to CSPP, and I'll highlight some new and upcoming geostationary products that we're working on or will be working on to transition them to operations. And similarly, I'll switch over to CSPP LEO, talk about some new polar products as well, and yeah, talk about some future directions and summarize. So this diagram kind of summarizes where NESDIS stands in the process. So we're between the science teams that design the algorithms, improve them, validate them, and operations that generates and distributes products. So we basically prepare these science algorithms to run in operations, so that can involve standardization, optimization, and quality assurance. And this diagram is kind of a more detailed breakdown of what that process looks like. So the red indicates the science teams, the research side. Blue is NESDIS, and green is operations. So once we receive the science code from the science teams, we have a series of meetings, demos, before we proceed to the actual integration work. Yeah, it goes through some more demos, documentation, before we actually deliver it for OSPO code review. And once we make the final delivery, there's some final testing and verification. And once it passes all those reviews, it is promoted to operations. So typically for a new algorithm, from the time we receive it to the time it's promoted to ops, we generally plan for a 6-month timeline, but there are a lot of things that can impact that. So we are usually working on many of these algorithms at the same time, and they can have interdependencies. So for example, if algorithm 2 depends on algorithm 1, and algorithm 1 has a delay, that's going to affect the schedule of algorithm 2, of course. And also there's sometimes that algorithm integration box can be much bigger in terms of relative effort and time. That can be due to code that requires extensive refactoring. Sometimes we run into problems deploying it on the cloud. Some like unique production rules that require us to develop a solution to get them ready for ops. And there's also some external factors that can impact schedules, such as if a new satellite has a launch delay, that can trigger a large amount of reprioritization and schedule shifts. But once the delivery package has undergone all these reviews and is promoted to ops, that's when it's ready to deliver to CSPP. Okay, so to switch to CSPP Geo specifically, previous deliveries have been focused mostly on the GOES ABI products that we deliver to the ground system. This is just a list of them. So we have the clouds, LST, aerosols, FLS, and winds. That has kind of expanded with products like the flood mapping. But these are just some examples of the framework-based deliveries that we make. So previous deliveries were mostly done within the Algorithm Service Framework, also known as the AIT framework. And the way that those worked is we receive a list of products that CSPP wants to generate, and we create a framework subset containing the product code, the algorithm code, and all the supporting ancillary algorithms, and put it all into one subset, so one executable. And we wrap that executable in Python scripts, create test cases, and then deliver it with all the test cases and documentation. And these are just a couple recent deliveries we made. So in 2024, we enabled GOES-19 support, as well as some science updates that Graham mentioned, like the cloud mask science update and the aerosols lookup table, I think AOD. And then back in March, we delivered a patch that enabled the generation of Himawari 9 clouds and winds with the new feature of being able to process the target region, Himawari level 1B. And these are just some cloud product examples of that target region. So yeah, I mentioned that there were some changes coming to the delivery process. So we're basically transitioning from the framework to individual standalone packages. So that will kind of work similar to how it does for CSPP Leo, where when each individual product gets into operations, we deliver it. So that will enable more regular updates rather than just having to wait for the full batch of framework algorithms to be in ops. We can deliver them one by one as they become operational. And these will be CCAPs, that's a cloud containerized algorithm packages. So they'll all be wrapped in the same interface. They'll be, it basically standardizes how each algorithm is run within the Docker containers. So all of them will basically be run the same way. The main difference compared to a framework delivery is that these CCAPs will need to be executed in order, like starting from the level 1B, going through the ancillary products and then the level 2 products. The framework used to handle that automatically, but as standalones, those tasks will have to be scheduled accordingly. So this is kind of a diagram illustrating that. So we start at the top with the geostationary level 1B dynamic ancillary data like the GFS, CMC, SST, and that gets put into a new CCAP that we've developed called Enterprise Dynamic Ancillary that processes all that data and provides them to the downstream level 2 products. So when we took the algorithms out of the framework, we lost the ability to split up the level 1B scene into different segments or chunks. So we've been working on some ways to optimize the standalone CCAPs to account for that. Firstly, we optimized the dynamic ancillary CCAP itself, basically only outputting the channels, resolutions, variables that the downstream algorithms need, which the framework didn't do. It basically generated everything, whether algorithms needed it or not. So that resulted in a substantial performance improvement, but to achieve similar performance to the framework, we needed some more optimization. So that is where this geostationary chunking project comes in. It's basically doing the same thing that the framework did with splitting up the scene, but it's more like a preprocessor that creates the chunks, and then at the end there will be a stitching step where it puts the full disk back together. So the processing will look exactly like this, but instead of full disk level 1B, it would be chunks, like one of these for each chunk, and then they'll all be put back together at the end. So that's the main changes coming to the delivery process. These are just some of the new products that we've been working on. We currently don't have plans in place to deliver these to CSPP, but if there's user interest, we can start those discussions to get them added to the list, possibly. So starting with like, the new products, we have a Volcat that will run on GOES, East and West, Himawari, MSG, and in the future, MTG. So our first delivery for that is targeting October this year. We also have NGFS, that's GOES East and West, targeting September. And we have the rainfall rate estimates, adding the MTG capability that was delivered last year. Then we have a new product, Surface PM 2.5. So our first delivery for that is targeting October 2026 for the Tempo instrument, and then GOES is following in February of next year. And yeah, another new product is Stereo Winds, and the first delivery supporting GOES and Himawari 9 is coming up in October. Okay, so switching over to CSPP LEO, we have delivered many algorithms that run on polar satellites like the JPSS, METOP B and C. This isn't a full list, just kind of a sampling. So we have a mix of framework algorithms like the clouds, aerosols, cryosphere, and land algorithms. And we recently added VIIRS fractional snow cover, which was delivered in April. And then we have several other standalone algorithms. So like I mentioned, for CSPP LEO, each individual product, once it becomes operational, we deliver it to CSPP LEO. So for most of the products, that procedure is not going to change. For the algorithms that were originally in the framework, it will add this additional pre-processing dynamic ancillary step to it. And we're discussing some training for any necessary training or support for the CSPP developers and science teams for running that CCAP, and trying to think of ways to make it simple and easy to use and incorporate into the CSPP software. So yeah, so this is a similar diagram for the CSPP LEO algorithms that were based in the framework. So yeah, it's just the same, like the polar level 1B and any ancillary products goes through enterprise dynamic ancillary. The only difference is with geostationary, we can treat some of that as static. With the polar satellites, we can't do that, so that will need to be processed every granule. So these are some new and upcoming LEO product implementations. So we have the Polar Oxbow SST for VIIRS and AVHRR, targeting November 2026, which will update them to the newest science version 3.0. And following that, we'll have the new version of L3S in February. And the Metamage delivery is in planning. A new product coming up is the blended ice motion. That runs for AMSR 2 and 3, VIIRS, and Metamage, and that is targeting April of next year. And the VIIRS SuperDAP products, the clouds, aerosols, land, and winds, will be adding the METOP SG and J4 capabilities, and those deliveries are still in planning. we'll also be adding METOP-SG capabilities to a handful of other algorithms, ENTOZ, MERS, SFR, VOLCAT, and NGFS. And also the gas product deliveries will be adding support for METOP-SG B1. And that's also in development and planning. So thank you. So to support both CSPP, LEO, and GEO, or LEO and GEO algorithms, we at ASSISTT have developed some standalone readers for MTG and MetImage. Those are similar to the level 1 readers that were part of the framework. So for algorithms that don't have their own readers for those satellites, they can use the output of these. So this mostly applies to the METOP-SG, like clouds and those algorithms. But there are a couple for MTG as well that will use these standalone readers. Okay, so to summarize, NESDIS is going to continue to help transition scientific algorithms from research to operations, including new products and adding new capabilities for new satellites like METOP-SG and MTG. And we will continue to collaborate with the CSPP, LEO, and GEO teams and deliver products of interest to their users and provide any support as needed to help the teams transition to our new delivery procedures. Thank you.
Thank you, Michael. Interesting perspective on how the NOAA algorithms make it to CSPP, GEO, and LEO, and a nice preview of what's coming up in future. So are there any questions for Michael?
Thanks for sharing some of the plans for especially the METOP-SG products. I noticed there was one line in your slides that said there's no plans for delivering any of those to CSPP LEO right now, unless there's user feedback. I'm sure there's a lot of people in this room that feel this way, but those products are extremely valuable in operations. So I'm just voicing that, yes, any of the ones that are in CSPP LEO now, especially the ones that have METOP-B support specifically, we know that satellite will be going away at some point, and having the SGA1 versions of those algorithms would be very important.
Great, thank you. Yeah, I think for both METOP-SG and J4 for the existing products, it was probably in the long-term plans to do that. It's just not like in our schedule yet.
So potentially a request could go to the ASSISTT team, is this possible? And the ASSISTT team would tell us yes or no.
Yes, Priyanka
yes,
her hand up.
Priyanka's right there. Okay.
I can add, the plans are there, and I know Lihang has already said the plans are there, but it has not made into our schedules yet because funding cycles and everything. So we are working on the plans.
Okay.
For both METOP-SG as well as J4.
We have time for one more question. Okay, thank you, Michael.
Thank you.
So our next presentation will be from Srinivas Desametti from the National Center for Medium Range Weather Forecasting in India, and he will speak to us on the topic of DBNet data usage at NCMRWF, status and plans.
Good afternoon all. So I'm from the NWP Center from India. So along with that, we also receive the data and process using all these software. So we are from starting to end. So I will present some of the our results also. So in that we receive data from we receive data from Hyderabad, that is NRSC, that is Remote Sensing Center, and also one more center in Hyderabad, that is INCOIS, where the ocean applications, for ocean application data has been received. So these are all collaborators. And from IMD, where we disseminate the data. So Dr. Shankarnath, he is a collaborator. So main where we started is our director actually has a forward vision to contribute meaningfully globally the data. That is actually earlier there was no data. So he started like we have to contribute globally. So he has contacted ISRO to receive the data at NCMRWF. So we have installed with the help of our our members, like especially from INCOIS, Dr. Pattaviramara Srinivas and all, and ISRO Aparna and IMD. And apart from that, we have international friends like Dr. Liam and Nagel and Simon Ruth Adim from UMedcast. So all these people are helping in this journey. So we are thankful to them. So in NCMRWF, initially we were receiving data from NRSC, but they were having only NOAA 18, 19. There is no 20 plan for them. So till last year, we were processing at NCMRWF. And INCOIS also having similar at that time, but later they upgraded with the NOAA 2021 and FY3D3. So now at present, India, only INCOIS data has been shared globally, and it is processing directly at INCOIS, the reception center. So, so the Hyderabad is located at this center of the India where the dish is there located. So almost Bay of Bengal and Arabian Sea, some parts it covers, but northern and southern parts still we miss. So this was the data which we have been processing earlier, and this has been disseminated through GTS. And these are the now NCM is the NCMRWF the name, and within COIS now it is INC. So these are the files currently has been disseminated through GTS, and these are all available for all the NWP centers. And right now they are being used. These are the headers from GTS. So feeds from the NWP SAF. So we can actually see the same headers. And for India, there are already like Delhi, Guwahati, Chennai, Hyderabad, and Hyderabad there are two. One is for INCOIS, another one is for the NRSC. So NRSC, NCMWF was processing. INCOIS straight away, INCOIS is processing, and right now it is disseminating. So these are right now you can see in the website. So this was the data, how we are receiving the data, the timeliness. So after receiving the data, within 20 minutes, it reaches the NCMRWF directly through dedicated line through GTS. And when at NCMRWF, we are processing all the data, many of all aware. So I'm just showing anyway, it's just. So at us, we have directly APP and the Metapizer and OPS LRS for IRZ. Apart from that, we have on the other side the CSPP and RT-STPS. So these two systems are installed in our HPC supercomputer, and directly when we receive level 0, we directly process, and the buffer files will be going directly to the data assimilation system, whereas the other like HDF, whatever the products that we are creating the images, visualization images, and these are being used by IMD for nowcasting applications. So these are some of the products generated using the data, DBNet data, direct broadcast data. So like Amphan is a cyclone, so it is very clear how for better representation, better visualization of the cyclone, and the AMSU and as well as NHS on the right hand side. So this will give you more the characteristics of the structure and as well as the intensity of the system. So these are very useful for nowcasting. So all the data has been used, and even the products. So data availability in the NWSurf monitoring website. So both we could see now they added even Hyderabad recently, the INCOIS station also. But now recently just data has stopped and they are working. So maybe probably I expect by this month end it will be disseminated again. Otherwise, the station is working fine. So from India, the data will be continuously disseminated. So, now we have received the data. Now how we are using it in the NWP, our global forecasting system, and as well as the regional systems. So these are the some of the passes a cyclone case I'm just presenting. So these are the passes of NOAA 1819. So we have over India, the 16 and 18 UTC passes are available. We don't have the other two cycles. Um, so this is one cyclone which happened to be in the Arabian Sea. The name is Biparjoy. It is extremely severe cyclone, and it has landfall over Gujarat. So the numerical experiments are designed, the control, and we received different sensors. That is ATOS, ATMS, Chris, ATMS, and ATOS plus ATMS. Mostly we were checking here the microwave radiances, how they are having impact in the NWP system. So it is actually the UKMATF is based operational model at NCMRWF. So we have run the analysis for 10 days, and then the forecast also any one cycle can be run for 10-day forecast. So simply to tell, so whenever we added the ATOS, that is microwaves, humidity and temperature, and ATMS, so both are actually having a better impact in the mid troposphere. Basically, it helps in reducing the temperature and humidity. That is what is missing in the conventional data. So the DBNet data, which will help that time. So this is actually helping the NWP to take care. So it is producing a better cyclonic system. So basically, the early run of NWP runs at morning 7:30. By that time, we don't receive the full data. So the DBNet really helps, especially the tropics or wherever any extreme severe cycle, any extreme weather system is occurring in the any of the region. So basically, the structure also getting improved by adding the microwave this data, DBNet data. And apart from the global suite that was in the global model, now because NCMRWF we run from 300-meter city model till we run the 10-day deterministic, which is a couple model now, and we have ensemble model. Apart from that, we have the subseasonal and seasonal. So total system is running at NCMRWF. So everywhere the data has been used, and this is actually regional HRRR system, which runs 18 hours forecast based on every hour. So even there, this data, because we are receiving within 30 minutes of data reception, so this data has been directly being used in the HRRR system. Otherwise, the main data which comes from NOAA or UMETCAS gets delayed a little bit because it receives some other location. So this is for another cyclone case. So it is also having a similar reception time, 15 to 20 minutes. So we have seen that in 2024 cyclone case, same, it is having full coverage here. So we have seen that because it's a regional system, up to 72 hours, it will have impact. After that, the dynamical system takes care. So here, if you see the structure, how the ATMS, that the experiment, basically the ATOS and the ATMS is helping to improve the intensity of the system. So basically from start, even here, the humidity in the metroposphere. So that is what it is helping. And both the systems have confirmed that its applicability is very good and it's important for extreme cases. So the plans for India now, I will just present. The present mission Mausam, Government of India has initiated a project, Mission Mausam, and a part of that, 2 DBNet stations. NCMRWF has been, started a project with government. So we are going, apart from the central India, whatever you have seen earlier, we are planning 2 more stations, one in the north, one on the south, 2 stations. One was will be in Delhi, NCMRWF in our operation center, the other one in the Chennai. So these 3 will cover most of the region, and this will give the application, both NWP, the nowcasting, all things will be covered here. And data sharing. So right now, if INCOIS data will be ready, then we also had discussion on 18th with Dr. Simon here. So we'll be developing the system and we'll be soon start sharing in the WIS 2.0. Already this data is already going through GTS. Now we'll be adding same in the WIS 2.0. Apart from that, so the present two stations, whatever we have proposed, end of this year, probably they'll be into commission. And plan is for next 10 years, it should work. Both L and X band and all the satellites, whatever currently they're available, we want them to get the data, receive at these stations. And we are having good collaboration with all scientific and as well as technical, all the partners, and very helpful for bringing this data, make it happen. So we are all thankful once again. So even operational challenges we will have do how we have to maintain the station and products with time, how to develop. So with the collaborations and with all of your support, definitely we will be doing good job and we will contribute. That is what we started the presentation. So we'll be more and more contributing to the global NWP and as well as the DBNet community. So after the two stations commissioning, so we'll have the full coverage, north the Delhi and south Chennai. So we'll have full coverage from north to south and east to west. So this will be the project. Some conclusions are we are receiving the data. Earlier we were receiving, now directly INCOIS is processing. And these data has been having very positive impact in NWP and as well as the application of these imageries are very helpful for nowcasting. And the two stations will be soon by this year and will contribute to the global DBNet community. Thank you.
Thank you, Srinivas, for the overview of your activities at NCMRWF. Are there any questions for Srinivas?
Yes.
Nick, please go ahead.
Thank you very much for your presentation. Very interested to hear about the two additional stations. I was looking at the NWPSAF DBNet monitoring, and I don't see any entries at the moment for any of the Indian.
Recently, the data last 1 week, there is some issue. Otherwise, there are HYD. HYD is the station, Hyderabad. So there are two already. I think when the data starts disseminating in GTS, we can see there.
Okay.
It is already added.
At the moment, there's only the Hyderabad station there, and it doesn't show anything from the Hyderabad station.
No.
This week.
The station has some problem.
Okay.
They will.
And when the other two stations come online, they'll report as well to the.
Yes.
Okay.
Yes.
Thank you very much.
Thank you.
Wish you luck with that.
Thank you.
Are there any other questions?
Yes.
In these new stations, I see that you are planning to get the METOP family satellites as well as the NOAA satellites, but I also saw you were gonna get FY3D and E from the Fengjun family. Are you planning to acquire from FY3EF and the newer satellites from this?
Right now, the data still we are processing. We are working on it. Only NOAA and the METOP and these satellites are being assimilated.
Oh. My question comes also because this, starting from FY3F, the new Fengjun satellites will start being left-hand circular polarization. And this has to do a lot with hardware. If you are planning to acquire this, you should make sure that the antenna can receive this.
Sure. Yes. Thank you. We will do.
Thank you.
Any other questions? Okay. Thank you, Srinivas.
Thank you. Thank you, Ms. and CSPP for this opportunity.
And also a reminder to please, again, please, if you have any questions for our discussion late this afternoon, please submit them via Slido.
Yes, and for the discussion, the last thing on the agenda, it can be a question, it can be a topic you'd like to discuss, it can be some small innovation you'd like to tell the crowd about. So please enter it in Slido. So let's move to our next presentation, and it will be perhaps jointly presented by Robert Stafford and Skyler Fennell from NTIA in the United States. And they will be speaking to us about NTIA efforts to protect meteorological satellite signals, past, present, and future.
Okay, hello, I'm Rob Stafford. This is Skyler Fennell. And we're with the federal government, but we're here to help, right? So, and we're radio guys. So we're gonna talk a little bit about radio. What will happen is the first piece is where we'll talk about our radio satellite receiving station. And then Skyler will talk a little bit about a project that our friends at NOAA were very forward thinking, and we've been working on for about the last 10 years regarding radio frequency interference into satellite signals. Then we'll go to a short project we just started on, the band studies. And finally, I'll talk just a little bit about something that's coming down the pike real soon, which may turn into a real problem for a lot of the direct broadcast users in the L-band. So let's get right into it. So we work at Table Mountain. ITS, well, let me do this. ITS itself is part of NTIA. So NTIA is the National Telecommunications Information Administration. ITS is the laboratory arm of that. ITS stands for Institute for Telecommunications Sciences. So you can see why we abbreviate all this. We can't even spell it. And what we primarily do is deal with government systems. So we're a little bit like the FCC, except the FCC is commercial systems. We deal with government systems. And to a large extent, that ends up being doing experimentation about interference into or from government systems. Our satellite stuff is in the Table Mountain Field Site and Radio Quiet Zone. Is one of 2 radio quiet zones in the United States. And this thing is about 12 kilometers north of Boulder. Our main office is in Boulder, Colorado. And so this was a slide our boss asked us to put in, which is a little bit more like a real estate advertisement than anything else. But it's 1,700 acres of really beautiful territory, and it'd be a great place to build a house and look at the mountains if only the federal government hadn't gotten to it first. So our field station is smack dab in the middle of this plateau. And what you see here is on the left-hand side, you see a radome that contains a 2.4 meter dish, which is what we use for things like POES and MEDOP. Then just to the right of that, there is a 3.7 meter dish, and that's what we use for DCS. Then sort of sticking out way in the back there is the RFIMS device itself, the thing that kind of looks like perhaps a Q-tip or something like that. And Skyler will talk a little bit about that. And then finally to the right is our 6.5 meter dish. We use that for GRB types of things. Our environment is good for testing because none of the information that we pick up from the satellites is used for anything except for testing. And primarily, we either inject interference into the satellite signals to see what happens, or occasionally we radiate interference so that we have the antennas as part of the system to sort of see how they cause difficulties. And to a large extent, in recent years, our interferer has been cellular technology, so LTE and 5G. And I'll give it to Skyler.
Okay, so now I'm going to get into the RFIM system, which stands for Radio Frequency Interference Monitoring System. So yeah, back in 2015, the FCC auctioned off the AWS-3 spectrum, which is uplink only. They designate it as uplink only spectrum. It's at 19. That should say 1695 to 1710. Guess I missed that, but yeah. So 1695 to 1710 megahertz is uplink only designated spectrum from a cell phone or user equipment, and they had the caveat that it has to be shared with the meteorological satellites. So 1695 to 1710 is the NOAA METOP, or sorry, the METOP satellites, METOP A and B, and then also the NOAA 1819. And there's a couple other, like the Argos and OceanSat runs in that spectrum. So the RFIMS was developed as a system that would actually receive those user equipment uplink transmissions and detect whether it's going to potentially be at the threshold to interfere with it, and actually report back to the cell operator that your tower is, or that your UEs that are connected to that sector are interfering, so you need to do some mitigation work. So basically that mitigation could be like telling that sector to completely turn off. It could be blanking out certain resource blocks, telling it, yeah, this satellite is using these resource blocks in the middle of the band, so turn off those frequencies, or just telling the UE to jump to a different frequency band to try to not interfere with the current low Earth orbit satellite pass. Okay. So the RFIMS problem statement. So as you can see in the photo, we're not getting all of the frames that are supposed to be received. So this is a picture from the GRB downlink. This was from our GRB receiver while we were injecting RFI. And this is what it could look like if you have 5G or LTE interference coming into your system. So the resulting RFI degrades the satellite imagery and potentially loses critical data. Okay, so the RFIMS itself. So this was developed by L3 Harris, commissioned by ITS, and then NOAA is the customer for this antenna. And we've got, well, there was supposed to be, what, how many RFIMS were? 18 22?
There were supposed to be 17 RFIMs sent to NOAA, and I believe it was 9 RFIMs sent to Department of the Interior, and didn't quite work out that way.
So currently we've actually have serial number 1 at Table Mountain at the quiet zone. And this is basically the test RFIMs. So it was kind of the perfect environment to actually test it. So it's a beamformed antenna array. There's actually 22 columns going around that top piece, and it can basically detect the direction of the signal and decode the uplink physical cell identity. So that's kind of the header at the very beginning of your packet when your cell phone is transmitting to the tower. And the magic in this RFIMS is that it actually can do it on the uplink, because usually you have to actually have the downlink from the cell tower, but this can actually, there's some algorithm that L3 Harris developed that can pick out that actual 3-digit number off the uplink. So it can't actually decode any of the cell phone traffic. It can't pick up your conversations. That's all encrypted. It just finds the header, and that knows, okay, that's what tower your cell phone is connected to. And we have a potential interferer. So now we can notify the cell operator that cell tower is now potentially interfering with our with the Earth station uplinks. And then it sends that data to the CMS, the Central Monitoring System, where we can actually look at the signals, kind of get a graphical view, which I'll go into on the next slide. So this is it's kind of a busy slide. There's a lot going on here, but This is a, on the x-axis, that's time. It kind of got cut off, and then the y-axis is frequency. So you can see kind of in the 1700 to 1710 area, that's where we're currently seeing an interfering LTE signal. And then at the very top right, the CMS picked up which PCI that is. So it saw 18 and 19. It saw interference at this particular time. And then this is kind of a snapshot event. This is only 16 milliseconds long, this event. And basically, it got reported to the CMS. And then now from there, the cell operator who happens to have a sector running at PCI 18 or 19 could basically turn that off. Okay, so now we're getting it into 1675 to 1695. So we're now moving 20 megahertz, the next 20 megahertz down from where I was just talking about. And this is new, I guess in the new Big Beautiful Bill or whatever they just changed the name to, they're trying to find another 500 megahertz worth of government spectrum to auction off. And I think the first target is this 1675 to 1695 band is what Office of Spectrum Management's kind of identified as the first thing they want to sell off, which is kind of unfortunate for the satellite operators. So as you can see here on this graph, we've got the DCS at the left-hand side, and that's around 79, kind of the edge of 1680 megahertz. Then we've got the GRB in the middle. That's like a 9 megahertz wide carrier. And then HRM1 is close to the top at 1694. So the biggest concern right now is the DCS, because that's just a bent pipe repeater. That's all those little meteorological like weather sensors, buoys, water level sensors, and coming down from that is there's no alternative delivery because it's just basically 400 megahertz up, L-band down. GRB and HRM1, that's already a rebroadcast. So as some people were talking about earlier, with the cloud delivery systems and some other ways, there are potential alternatives for HRM1 and GRB, but not really for DCS. So that's kind of where we've been focusing the beginning of these studies. And I think also OSM identified 1675 to 1680 as the first 5 megahertz to potentially think about relocating. Okay, so this is a frequency-dependent response investigation, kind of a typical way we test stuff. We inject a 5G interference signal, which is that large wide signal, and we kind of sweep it up and down and basically chart the responsive curve. So this is looking at our spectrum analyzer coming off the DCS receiver, and then we've piped in our own LTE signal on top of that. And now we're just sweeping it through and looking at the resulting interference to see what actual power level causes outages or issues with the transmission. Okay, I'm going to turn it over to Rob. He's going to talk a little bit about now potential future uses of the spectrum, including satellite constellations.
Yeah, so this kind of qualifies as future work. We're just starting to look at this. And the difficulty is the system that we talked about first, the RFIMS, was designed to help protect the 1695 to 1710 spectrum. That spectrum was designed to be, or was originally declared to be shared, and a company that Dish Networks bought that spectrum and were allowed to use mobile phone uplinks, the signals from the mobile phones themselves, in that spectrum. Well, they never really ended up doing that, and now they have sold that spectrum. And I won't mention the company that they sold it to, but let's say that they are the stars of the constellation business with over 10,000 satellites in their constellation right now. So you can probably sort of figure out who it is. In any case, their constellation is primarily satellites that are of a class called DTD, or sometimes it's abbreviated D2D, which is device to device or direct to device. And so most of their satellites broadcast straight to data terminals on the ground, and the data terminals broadcast back up. However, we're more interested in a small subset of their constellation, about 600, a little bit more than 600 satellites. And these are called DTC or D2C. And those satellites broadcast directly to cell phones. And normally this would not be too much of a problem, but because of the frequency range that they may be going into, this may turn into an incipient problem for us. Power coming out of these satellites is about 88 dBm. That's the EIRP from the satellite. By contrast, for example, the power coming out of the METOP satellite is 54 dBm. So this satellite has about 1,000 times greater power. These satellites also are at 350 kilometers altitude, where of course say GRB is at 35,000 kilometers altitude, so about 100 times further away. In addition, since this is a very large constellation, it's in 2 different orbital planes. So when we take a look at what happens at our Table Mountain site, for example, on average, we see 25 satellites in any given instance. And that would be a real problem if they were in our frequency range. Luckily, these folks are kind of in partnership with T-Mobile, and they're working in the 1995 megahertz range. So they're outside of our frequency range right now. Around here, it would probably be Deutsche Telekom that they would be working with. However, they purchased the 1695 to 1710 spectrum, and they are looking into purchasing the 1675 to 1695 spectrum. So if that in fact does happen, then what we may get is base stations in the sky coming overhead every 90 minutes. They have 90-minute orbital periods that are putting out a considerable amount of power. By the time the power hits the ground, the satellite power will be about 10,000 times as high as METOP's power, and it will be about 5 million times as high as GRB's power. So if these things end up in our frequency range, we're going to end up with a real of a power issue. This is what the DTC constellation would look like from Table Mountain right now at this instant. And this is what it would look like from here. So you can see that there are an awful lot of satellites. All of these, the green lines are satellites that could make a connection here. And all the little blue dots are the rest of the satellites in the DTC constellation. So there's a considerable amount of satellites. There's a considerable amount of power. And there's a real potential that that power may end up in our frequency range sometime in the near future. We don't know. The power that we have is NTIA. The power that we have is NTIA is we can sometimes suggest to the FCC what they should allow and what they shouldn't allow. Strangely enough, sometimes they even listen to us. Not all the time, though. So we are working to make sure that, to the extent that we can, that we don't develop a problem for the direct broadcast community because of this satellite network, and we'll have to see how it goes. This study's only been in operation for just a few weeks now, and we're going to have to wait and see where things head. And I believe so. Closing thoughts. So we, of course, want to acknowledge the support of NOAA for RFIMS. And in the past, the past project was RFIMS determining the physical cell IDs from phone transmissions. In the current work, we're doing the band studies work to try and protect DCS. And in the future work, we're trying to think about what may happen with these base stations in the sky. So at that point, I will thank you very much and ask for any questions.
Thank you, Rob and Skyler, for that interesting presentation on spectrum protection. So are there any questions from the audience? Yes, great.
Thank you for that presentation. I think this is a really important issue, and I'm very happy that that you bring it up. This is a group that stands to be significantly impacted by that. There's a lot of questions, I think, a lot of discussion we could have on this topic. I want to make the point that, to me, the argument that GRB is less important because there's an alternate means of distribution of the full resolution data via the cloud kind of misses the point. There are, people know that there's other ways to get data, but they choose to get it via GRB for a number of reasons. So I think it's important that that be considered. So thank you for doing this study. It sounds like, if I understand correctly, if the study if everything that you're telling us about the massive power of this of these signals impacting streams like GRB, what you're kind of expecting to find comes to fruition, you'll pass that information on to FCC, and then there will be some determination made. Okay, so that's kind of the process that we're talking about. Okay, yes.
Yeah, I completely agree with your observations. The GRB has so many products, and it is so vital to so many things. I think that what is going on among the powers that be, perhaps in Washington, D.C., is that since GRB downlinks many of its products, and then those end up on the internet, and the feeling is that these are not quite as time sensitive as the DCS product, which is strictly a bent pipe repeater that does not end up on the ground before it comes back up to the users. I think that's their rationale. But of course, this is Washington, D.C., and their rationale isn't always the way the logical people think.
And then if I can ask a follow-on question, what is the geographic scope of the spectrum sharing? Is it scoped to continental United States? I mean, you showed a map of Europe, but I assume that was just for comparison purposes.
So a lot of it's going to depend. So like if the 1675 to 1695 gets used as uplink spectrum only or downlink, but then, yeah, a lot of it would depend on, like, let's say it was sold to a satellite operator for only the US, then it would be a US problem. It kind of, because the way, like, for instance, Starlink works is they shift bands as they go over different countries. So it would depend on, so we're only really talking about the US right now. Things could be different over here on what bands they end up using for their direct-to-cell downlinks. But if it's uplink spectrum, then the way they would probably do it is they have a protection zone where all of the known Earth stations that they want to protect would have like a certain radius where they don't have cell towers running that, or where they don't have user equipment running that spectrum or something like that is what the criteria would probably look like. But yeah, I mean, the problem is this is so open-ended that they haven't even told us, is this going to be like uplink spectrum, downlink? What's it going to be used for? They're like, we just want to sell off spectrum right now. And it's like, how do we even study this? So that's kind of an issue right now.
Time for one more question. Nick.
I'm very interested to see how DCS fits into all that, because I'm responsible here in EMSAT for the DCS. We worked with Skip Dronen and Bo Backus, looking at those things. But maybe I'll take that offline and talk to you in the coffee break. But thanks very much for your presentation.
Thank you.
Thank you, gentlemen.
Thanks so much.
And thank you folks for a great user group meeting so far.
So let's move to our next presentation, the last one before the coffee break. And that will be from Toby Hutchings from NOAA in the United States. And Toby will speak to us on the topic of future plans for NOAA NESDIS direct readout.
All right. Can everyone hear me? All right, good afternoon. I'm Toby Hutchings. I'm from NOAA. That previous presentation was a perfect lead in to where my branch has issues, I should say. That's the best way I'll sum it up. Anyway, introduction to what we do. We're the direct services branch. And there's a myriad of services we offer at NOAA. It's GOES DCS, which you guys have heard already, Argos, H1N1, GRB, HRD, GNCA, and believe it or not, also SARSAT. So what we're dealing with now is the shifting paradigm. What we've all come to know, direct broadcast as a service in the past, there are a lot of outside parameters that are changing it. Like I mentioned here, direct satellite services will no longer be hosted on the next generation of the GEO satellites. That provides an opening for, in my opinion, the sale of potential frequency spectrum. So for our branch, our job is to try to find a way to utilize commercial technological advancements to meet the evolving requirements of our missions, but also we have to make sure that we can provide a dependable solution to the direct readout community. This is a notional diagram from probably about 2 years ago. And at a very high level, you see the GeoXO satellite on the left at the top there. That part doesn't change. That is downlinked, processed on the ground, uploaded to the NCCF, which is NESDIS Common Cloud Framework. And from there, it would go to a commercial satellite for broadcast. Our broadcast, the services that are basically that will be impacted by the potential sale of frequency, the removal of hosting on the satellites. It's been broken down into two separate streams, a high rate stream and a low rate stream. And here are the equivalents. The high rate service. It's basically what we all call GRB now. It's the instrument data collected via GOES, downlinked to NOAA, processed on the ground, and uplinked as GRB. It's distributed on the L-band. It's a hemispherical broadcast, dual circle polarization, 31 megabits per second. It has the ABI imagery, GLM, and some space weather data on it. The proposal for the GEO high service, again, would be instrument data collected via GeoXO, downlinked to NOAA, processed in the cloud, distributed by the NCCF, which is the Common Cloud Framework, and selected products passed to commercial providers, uplinked to a commercial satellite. The notional bandwidth that we have been initially given was about 50 megabits per second. What frequency that would be in, we have to do the research to find out exactly where we stand. That's my reason for the trip out here. I've already spoken. Thanks, Nick, for introducing me to Daniel yesterday, because UMETcast would be a very comparable architecture to what we're trying to accomplish. We also have GNCA, which I mentioned earlier, which is our own broadcast. But honestly, that hemispherical direct broadcast from a GEO satellite seems to be going away. And I don't know if there's anything we can do to try to stop it, which that's why we're trying to get the word out as much as possible. It's a very I won't say alarming change. It's a change that we have to mitigate. And that's why I'm here, because from our branch, we have to mitigate all the possibilities and the risk of no longer having that hemispherical broadcast from a geo satellite and its impact to our users and to the user community. The other service, by the way, is the low rate medium service. That's H-M1, and that's L2 products from GOES and from other partner satellites packaged into a data stream. It's very useful. We have partners in the Caribbean, partners in South America, Central America, and they actually rely on this broadcast more than we do CONUS in the US. And it also has the M1 alerts, and it's about 40 kilobits per second in data transmission. So in the GeoXO era, the goal is to create an equivalent to it. But again, the issue will not be what's in the data. Our biggest obstacle to this point has been trying to replicate that hemispherical broadcast. Because for this data, especially this low medium rate data, we have users that are sometimes in the maritime community. They could be out in the ocean. What we've come across so far is that most providers have done beam shaping, and they're making their broadcasts fit land masses because that's where people are at, which makes sense. So this has been, it's been interesting. We're just starting on our part of doing research, commercial research, trying to get as much information as we can to try to find a solution. And we started, we'll call it in-house, by speaking with the contractor or the provider we have for GNCA, just to ask him, hey, if we wanted to expand, what would that look like? What do you guys think would be possible with the technology out to date? We've gotten some input. Some's interesting. Some of it's initially would think, oh, wow, that's kind of far-fetched, but it's like, you know what? We found ourselves in a pickle where all possibilities were open to, and we're just trying to find the best, again, like I said, for our requirements at NOAA, and to make sure that we can provide a service that the user community has come to rely on over decades. That's really it in a nutshell from me, because I don't have any information as to what these services will look like, because we're still in the discovery process in our branch. Hopefully the next time we have one of these meetings, we'll have more information as to maybe a direction we're leaning. We don't have RFIs out yet. So again, like I said, we're still in the fact-finding, information gathering portion of this process, and for our branch, in case anyone has questions. So it would be easy to reach out if you have questions about Argos, GRB, HRD, or SARSAT. It would be me. It's my email address. For H-M1 or GNCA, it would be Ian Averick, and that's his email address. And for Ghost DCS, it would be Skip William Dronin, and that's his email address. And from the previous slide deck from the NTIA guys, yeah, Ghost DCS isn't impacted because it's still hosted on the spacecraft. That's the difference between Ghost DCS, GRB, and H-M1. It will be hosted on the satellite, so it's being hosted on the satellite affords it protection as a government data stream. Any questions?
Thank you, Toby. Are there any questions?
This is a question from Slido from Wanping. Will GeoNetcast be kept for GeoXO?
GeoNetcast isn't a service from GeoXO per se. It's a service that actually has data from geo satellites. Sorry, got too comfortable. It's data from geo satellites. It's data from LEO satellites. It's data from our partners. However, it's having its own issues because of the potential auction of C-band, which is the broadcast for GNCA. So that's another issue. It's another risk that we're mitigating in our branch at this moment. So we'll keep you posted, but it's not part of GeoXO, so I'm not going to say it's going to go away. It's actually the first service that we have that's being impacted immediately. The C-band auction, we have dates, we have times, and 2027, if memory serves me correctly, is the auction date, and we're trying to mitigate that as we speak.
Well, Toby, on one of the slides you showed, it mentioned a data rate of 1 megabit per second for I think a GeoXO rebroadcast. Was that correct? Maybe even the previous slide. Oh, no, the next one. Keep going. Next one. Next one. Oh, I think we're going
the wrong way?
Yeah, I want to go backwards. That one. Okay. So on the bottom right, it says broadcast service TBD band approximately 1 megabit per second. So that wouldn't be a replacement for GRB, would it? Because GRB
No,
data rate.
this would be H-M.
Okay, all right, it's
Yeah,
the low
see,
rate
yeah.
service.
I should have put an arrow between the two
Gotcha.
columns. Yeah, this would be
Okay.
the equivalent replacement for H-M.
So then there would be a high rate service.
Yes,
Okay. Okay.
50 megabits per second.
Got it. Thank you.
Thanks for this presentation. Very interesting. Have you done trade-offs of the existing use of L-band versus future use of commercial bands like KU band for looking at the system availability in case of tropical storms?
That has been our argument. We have tried to defend our position with use of L-band. What puts it outside of our scope, if I can be frank, is that if it's no longer hosted on the satellite and it's contracted out as a commercial service, then that in essence is NOAA saying that it's vacating that frequency band. It gets into politics. I'll be point blank. And this is where it gets difficult for us. Our branch, myself, Ian, and Skip, we unofficially have been tasked with defending NOAA's use of L-band, C-band, X-band, and it's only so much we can defend because we get inundated with questions. We try to gather, because it's more than just NOAA, by the way. There's other agencies federally that are using this data to complete their missions. And our goal has been to find these cases, whether it's state, local, or even federal, find these cases, get them to present their stories to the FCC to try to derail some of these plans. And like I said, it's more into politics and further away from engineering. So yes, we have looked into the fact that, there's a trade-off when you get into like potentially using, into the K-band and dealing with rain fade and tropical storms, and the previous presentation about GRB, you can get it from the internet. We don't agree with that. From our position, from our branch, we wholeheartedly disagree with, it's available on the internet. Yeah, because if you have power, you can have internet. If you don't have power, you don't have it. It's a long story. It's an argument that we are prepared, and we have been having for the last year and a half, 2 years. We're fighting the fight. We think this is important. We think this community is important. We think the collaboration between us and all the other agencies, it's important on a global scale, and it's more than just, hey, this works for us. So we are trying. And again, my email's at the end of this. Anybody with any information that you want to reach out, we're open. We're taking it from all sources, from anybody, because we are trying our best to keep these services available for the global community. And my emphasis is global community.
All right. Thank you, Toby. So we'll be moving to our coffee break. We'll start a little bit early, but we'll still reconvene at 15:50. Just a reminder, if you have a topic, a question, and piece of trivia you'd like to contribute for the technical discussion at the end of today's presentations, please upload it to Slido, and it's the top QR code on the handout that you received yesterday. And there it is on the screen. How about that? Do you have anything in the queue already, Jess? Can you see anything?
Yes, we have one question already, so.
Well, let's
We would appreciate
try
some
for
more.
5 at least. How about
Okay.
that? All right, well, we'll see you back at 15:50. So let's begin our final session of presentations for today. And we can get that session started by calling on Mikael Rattenborg, a consultant for WMO, who will speak to us on a topic of interest that's near and dear to his heart, which is the status of the WMO-coordinated direct broadcast network for real-time acquisition, processing, and fast delivery of satellite direct readout data. Mikael.
Thank you very much, Liam. I think after this presentation, you will know enough about DBNet for me just to be able to shorten the title of the presentation on to status of DBNet. I don't have to always mention in the title what is actually the objective of DBNet. So I'm working as a consultant for the WMO space program on DBNet. I've been doing that for quite a few years now. The concept and objectives of DBNet, many of you probably knows about this, but the idea is to have a globally coordinated system for acquisition, processing, and distribution of direct broadcast products, in particular for numerical weather prediction. And we use global consistency by using the common software, APP, CSPP, the FY3 processing software from China. And oh, it's also I was just worried that it was only me who couldn't see my slides.
Okay.
So ensure that the globally coordinated network of stations use common software, common configurations of those software, standardized coding and file naming, a global concept for quality monitoring, etc. So to ensure that all these DB stations work as an integrated network. Of course, since our main customers are the numerical weather prediction centers, the dissemination is done by the WMO information system feeding this. Used to be called GTS, now it's increasingly called WIS 2.0, WMO information systems. It's coordinated by the WMO spec programs, but of course it's supported by the CGMS operators, in particular by the direct broadcast operators, NOAA, EUMETSAT, and CMA. We established a target when we started this initiative in 2004 of covering 90% of the globe and making these data available on the GTS within 30 minutes. We have strengthened this target to 20 minutes because of the evolving needs of the short-range numerical weather prediction. And we say that for the ATOF suite of instruments, we achieved this goal in 2017, 10 years ago. And this is just an example of the coverage for ATOFs. This is now a few years old. I have some more up-to-date coverage plots a bit later. So the components, as I said, it's a global network. We have a loose structure of regional networks and sub-regional nodes, but we have some key entities involved in setting up and operating the network. We have EUMETSAT. You heard about EARS yesterday and the activities of EUMETSAT in setting up their new regional services. We have JMA and BOM, who are key entities in the Asia-Pacific region. There are other operators in the Asia-Pacific region, but JMA and BOM have a loose coordinating role to ensure that all the stations are working together. And in South America, the key players are INPE, the Brazilian Space Agency, and CONE, and the Argentinian Met Service. And last but not least, NOAA. We have the very significant contributions of NOAA and SIMS for a long range of direct broadcast stations. We have a coordination group that is working mainly in an online fashion, but at least 2 years ago, we managed to meet face-to-face in Melbourne, Australia. There's a nice picture of the participants in that meeting. There are a few faces that are also present in this meeting. Processing schemes is very standard. We have a software suite composed of APP, CSPP, and FY3P, and we have buffer converters to converting the data into the format which is used by the NWP centers. These buffer converters are integrated with APP, but that's just an implementation issue. We use two different schemes. We use centralized processing for some stations where the raw data from the station are provided to a central site. And then we have local processing schemes where the actual processing of APP and CSP is done by the station. And then I said the main distribution to the NWP centers is with GTS, but EUMETSAT is also disseminating the DBNet products on EUMETcast, serving all the European users. We have set up a monitoring site, which is very interesting also for other users of DBNet software. It is provided by the Numerical Weather Prediction SAF, funded by EUMETSAT. And down here is the link to the monitoring site, where you can look at the status of the processing from individual stations for individual instruments. You can look at data reception status. You can look at consistency with global data. A comparison is made by the NWP staff of the data against the global data sets, and flags or traffic lights are provided in case we have major deviations between the locally received and the global data. We also provide timeliness monitoring, so looking at individual stations, individual regions. You can look at the overall timeliness. This is just an example from a specific day in August 2025 of the timeliness distribution for ATMS. So again, to look at issues related to specific stations that are suddenly having timeliness problems due to whatever, communications issues, other issues on the station. We're providing operational services primarily from the sounding missions, so the ATOF suite of instruments, even though the ATOF is getting smaller and smaller, but we still call it ATOFs. Then we have, of course, ATMS from the JPSS satellites, and so SUMI and PP, and we have the hyperspectral infrared sounding data from CRIS and YASI. And I would say these are the really operational services. Then in a more limited extent, we're providing data from the FY3 satellite instruments, MWTS, MWHS. And then for specific regions, we're providing data from VIRS, AVHR, AIRS, ASSISTT, and the microwave imagery from the Chinese FY3 satellite. This is an example of the coverage charts, most recent that we have, provided in December 2025, courtesy of EUMETSAT. And you see here all the different DBNet stations and the coverage achieved for the instrument for ATOFs, CRIS, ATMS, YASI, and FY3 VAS. And you can see a common feature is that we have coverage issues over the Southern Atlantic, Central Africa, Northern and Central Asia. And we are working together with possible DBNet operators to fill these gaps. We have had some very useful additions to this network. One issue I can point out in the Southern Pacific Ocean, we have a station on Easter Island, which due to lots of cooperations between different players is now providing data for both ATOFs, ATMS, CRIS, and YASI. And that's, of course, in a completely data void region, so it's extremely useful data. We also have an interesting station in the Atlantic, which is Ascension Island, which you can see on ATOFs. Unfortunately, the capabilities there are more limited, so they're only providing ATOFs data at the moment, but hopefully there can be developments in this area. We are working at the moment on a transition from GTS to WIS-2. We're taking this as an opportunity to provide additional data that are not possible to disseminate by the GTS. And one example here is the full channel sets of YASI and CRIS from a range of stations, which are the stations indicated on the diagrams below. We are providing full channel sets, so not a reduced channel set like what is the baseline on the GTS, but actually a full channel data set from YASI and CRIS, which is made available already now via WIS.2. So any entity that is registering or subscribing to transmissions via WIS 2.0 can actually access these data as we speak. And of course, the ambition is to extend this to cover all other regions as well. So we're working on DBNet coverage extensions. This is just a summary of the main issues. The Argentinian services are thinking about or are in the process of establishing a high latitude station, so southern latitude at the Tierra del Fuego. Environment Canada are working on adding stations in the northern part of Canada, Inuvik and Iqaluit. China is now coming back into the DBNet network. They have been out for a while. They are now looking at integrating the data from 4 stations across China, using a new scheme that has been developed by China for cloud processing. The idea is that the processing for the DB data is not done on premises. It's not done at the station, but it's done in the cloud. And then the raw data are provided to this cloud processing instance, which then generates the final products for distribution. And that's a very interesting scheme, which has a number of advantages, in particular for the FY3 satellites. Then India is coming back into it. They have a project of renewing the DB stations in Delhi and Chennai. And finally, there are talks about how Russia can get back into the overall system. For obvious reasons, they have not been part of the international cooperation for a while. SEWA, we heard a lot about SEWA, and we're working on a continuous basis with the SEWA project to integrate in the future the 4 stations in Africa as operational DBNet stations. Of course, we will soon have a new DBNet station on the Azores, the Santa Maria station for METOP SG, which is an interesting addition in terms of the geography. And then the Sodankala station that we also talked about earlier. So these are main areas where we're working on increasing the network. This is just a statistic on the usage of DBNet products by the NWP centers. This was a survey done by the International TOFS Working Group, ITWG. They asked 24 NWP centers about their usage of DBNet data, and the conclusion was that all 24 NWP centers used DBNet data. Then we asked them which of the instruments were they using, and you can see a quite clear trend that the microwave sounding suites are the most mature. They are used almost by all NWP centers. Then comes the infrared sounders, which are slightly less used due to a number of issues related to, of course, to the assimilation, which is more complex than for the microwave sounders. And further down, you have the data from the Chinese satellites, MWHS-2 and MWTS. But in global terms, you can say that the usage of both microwave and infrared sounding data is very mature with the NWP centers, which is very good. And we are maintaining a strong coordination with the NWP centers through the ITWG, but also through other groups where the NWP centers are meeting. Sorry, I was going back. Okay, this is just recent timeliness statistics where you have provided by the NWP SAF. On the left panel, you have the delay statistics for ATMS from DBNet stations across all 3 ATMS satellites, NOAA 2021 and SUMI NPP. And on the right panel, you have the corresponding statistics for the global data from the same 3 satellites for the same time period. And of course, you can see that while we are achieving 90% coverage for DBNet within 20 minutes, the global data only achieve 90% availability within 1 hour, 33 minutes. So quite clearly showing the benefits of DBNet for short-range NWP. The same for YASI. Here you have the panel on the left showing the delay statistics for YASI from METOP B and C aggregated. And on the right panel, you have METOP B and C. You can see here that the global statistic shows 2 timeliness maxima because METOP is one of the METOP satellites is dumping twice per orbit, and METOP C is only dumping once per orbit. So you have a much longer delay, average delay in the provision of the data. We are implementing a pilot level 2 product service. We've been talking to certain regional NWP operators who do not have the capabilities of assimilating level 1 products. And there's been an interest in getting access to level 2 products that can be used for regional forecasting. And we had some discussions about how to start this up. And we have therefore started up a pilot service provided by SIMS, where we're providing a small selection of CSPP products that we think are most suitable for regional NWP, regional forecasting, which is the NewCap suite and the MIRS suite, so the infrared suite and the microwave data from a number of satellites. And SIMS is providing this data from 19 and 23 stations. The idea is to make these new data available via WIS 2.0, which would enable regional Met services to have a much easier access to these data than what they would currently be able to do. And then when we have start publishing this, making this more publicly available on WIS 2.0, we can start having a dialogue with the NWP operators, whether that is the type of product that they need or whether other products would be relevant as well. This is just the JPSS, but you know all of these. This is the NewCap suite of products providing profiles from a number of parameters for both atmospheric, both for weather prediction and for atmospheric monitoring. And the microwave integrated retrieval suite, MIRS, providing a number of other parameters derived from the microwave sounders. High priority DBNet activities in the coming years. The migration to WIS 2.0, it's important. It's coming from the outside. It's not us driving it, but we take an active part in this and try to use it for providing additional data that are not currently available because of the constraints of providing data on the GTS. And then the different regional geographical coverage extensions. These are just a repeat of the areas I provided in the previous slide. Moving forward with the implementation of FY3. FY3, as you saw, has a very limited coverage. It's currently only provided by EUMETSAT, but we think the new cloud processing scheme of CMA can be a very useful vehicle for integrating other or providing FY3 data from other DB stations. METOP-SG is a big challenge, as you saw from Nigel Atkinson's presentation yesterday. The local processing for METOP-SG is from a system point of view, challenging. And we're trying to work with the different station operators to look at their plans for implementing METOP-SG and try to support them in any way possible. Some of the new satellites have different downlink characteristics, so we need to develop the ground station receiving infrastructure. It's not the processing side, but the receiving infrastructure to be compliant with JPSS 234, METOP-SG, FY3, etc. That's also a big challenge in some areas of the world. The hyperspectral sounder services continues to be a focus. We want to make sure that we move towards having these services from all stations, using the WIS 2.0 infrastructure and try to find ways of increasing the uptake by the NWP community. The NWP SAF, funded by EUMETSAT, is working very hard to enhance the monitoring tools for DBNet, which, as I said, are also of general interest to DB users because it's indicating problems, issues with the DB processing that might be of a more general nature and is also of interest to other DB users. And of course, we are working on low product latency for NWP. So we are looking at all possible ways of reducing the DBNet product latency, doing processing of the passes as the passes arrive, for example. All these discussions we're also having in the DBNet context, or try to see how we can reduce the latency of the DBNet products to meet the increasingly challenging requirements of NWP. And I can make a little bracket here of saying AI, because we don't know much about what AI will mean for for data. But one thing we do know is that it will push the requirements for data latency. Once you have data-driven AI models, they will require very fast access to satellite data. So improving the data latency is becoming a key issue in the future when serving AI-based models. Thank you. Thanks to Liam for his leadership of the DBNet coordination activities, the coordination group members, all the operators, there are many of them in very different parts of the world with very different challenges, and they're all working diligently to ensure the overall services. And Zoya Andreeva, from my colleague from the WMO space program, who's doing a lot of work in ensuring the coordination and maintaining the web pages. There's some very nice web pages for DBNet at the WMO website that should also be consulted. You can easily find them. Thank you very much.
Thank you, Mikael, for your overview of DBNet. Are there any questions for Mikael? We have one right here.
I saw that Central Mexico is not covered. What do you need to have a station? Because we have a station actually, but to join DBNet.
Well, you need to make sure your software for processing remains up to date. You need to go into a validation exercise together with the NWP staff, together with the DBNet monitoring group, where you provide your products to the NWP staff, and they check whether there's any issues with the consistency of the data. But it's mainly a commitment to, on a best efforts basis, we're fully aware of that. There is no truly operational commitment, but a commitment to continue working on a best efforts basis to make sure that the configuration of the DB software suite, so APPs, CSPP, possibly the Chinese software, if you plan to use that, is up to date. Occasionally, the monitoring team will point to specific issues with specific stations, and then we expect that the station will act on these issues and provide them. So we go into a validation exercise. We have talked in the past about Mexico because it would be an interesting addition to the network. I don't know if Liam has any.
There might be another way that Lanotte could contribute to DBNet, which is already used by a number of DBNet providers, and that's that they work with SIMS, with our organization, to provide the level 0 data. Mm-hmm. And as long as the level 0 data are pushed to us with, soon after the pass, we will take care of all the processing and the conversion to buffer and the delivery to GTS. So let's talk offline about how to make that happen.
Yeah.
Thank you.
But it depends on the model you want to pursue, because we know that a number of station operators have a strong interest in maintaining abilities to process the data locally, and they don't just want to base the integration on providing data to a central site. There are different models that should be pursued here. But of course, Liam is the perfect person to discuss. Antoine?
Yeah, I have a quick question. And you mentioned that EUMETSAT provides the FY3 services, and I was just interested to know historically why the contribution to GTS with 2 for the Fengyong 3 was done only in EUMETSAT. So why other countries didn't follow up? And you mentioned as well this option of CMA cloud processing, that just to see if you have a list of countries interested as well to use this new platform for Fengyong 3.
I didn't catch the first
question.
question.
The first question was briefly, for historical reasons, why is I shouldn't say for historical reasons, why is EUMETSAT the only provider of FY3 sounder data within DBNet?
Well, you have to ask EUMETSAT. I mean, historically, there's a strong cooperation between EUMETSAT and CMA. There's a cooperation agreement between CMA and EUMETSAT that enables the agencies to exchange very detailed technical expertise on these. So it has enabled EUMETSAT to implement. The main issues that affect the distribution of FY3 software is security requirements, because the software is distributed as an executive, not with source code. And that is causing issues for a number of agencies. I think EUMETSAT has found a secure way of dealing with the Chinese software, but a number of other agencies have issues with this. And that's the reason why we discussed with CMA to pursue the cloud processing route, because then the software would not have to be installed at the premises.
So I think there might have been a second part to Antoine's question, but we might have to pursue that offline because we're a little behind schedule. But anyway, thank you, Mikael. So we should move to our next presentation, which will be from Dima Rashkovetsky from Ororatech, based here in Munich. And he will speak to us on a low latency, direct broadcast enabled multi-sensor framework for global wildfire intelligence. Dima.
Thank you very much. Thank you very much. I will try to focus more on the use case. We've heard the use case of wildfires from Alejandro, I think, yesterday, but yeah, I always feel like a bit of an imposter here because we don't deal with antennas, we deal with what comes afterwards. But I think it might also be interesting. So I don't think I need to explain why wildfires are important, but this is really what we at Ororatech are focused on. That's our only goal, to detect as many fires as possible, to notify people as fast as possible, because they are causing a lot of issues, whether it's climate emissions. They're responsible for roughly 10 to 15% of all carbon emissions. They have a tremendous economic impact. Of course, human lives are affected, and the costs of mitigation of wildfires are just increasing with every year. So when we speak about the Global Fire Intelligence Service, we really are global. We're not that small, and we're not that young anymore. I used to call us a young startup, but we are 8 years old. Now we have 500 users, over 25 countries, and we monitor 500 million hectares of protected areas. It's a bit misleading, this map, because wildfires don't really care about borders or geopolitical situations, and this is also how we try to look at it. We really want to work with everybody and try to alert people everywhere. And sometimes it's really frustrating when you see a fire and you don't have anyone to tell it. What do we do? So we combine fire detections from 35 satellites. More than, I think, 26 of them are publicly available. And this is also, we are really standing on the shoulders of giants such as EUMETSAT, ESA in general, NOAA, CMA, JAXA, etc. Because without them, we wouldn't be able to launch our own satellites. We wouldn't be able to understand the problem, and we wouldn't be able to tackle the issue and know what to do when we had to do it. So we have also launched our own satellites, and the reason we are launching our own satellites is because the currently existing satellites, they have a significant gap in their observation. Most fires start in the late afternoon, and this is not covered by polar satellites. So the only covering satellites are geostationary, with the acceptance of Fennell 3E, which is a unique orbit. I'll get to it. So right now we have thermal imagers, and we have 18, it should say actually, well, we have 18 payloads in orbit, and we have 14 satellites in orbit of our own. And we are observing the afternoon gaps, and we're also observing the morning orbits, because there will soon be no MODIS, unfortunately, and we want to be able to still provide the service there. Our products are level 1, what we call NRT active fire, so near real-time active fire. Currently, we don't offer yet fire radiative power, but this will come soon. and also land surface temperature and sea surface temperature. We want to cover the entire cycle of fires. So we mainly are focused on active fire detection, but we also developing tools to improve prediction, so risk assessment, short-term fire hazard, and analysis of conditions that actually support fires to start. Then early detection and monitoring, and also what happens after the fire. So the post-fire damage analysis and effects, how severe was the damage, and how fast the regeneration can actually happen. So as I mentioned, what you see on the right is the peak burning period of wildfires globally. And this is really not covered almost by any satellites. You can see on the left, these are the orbits. It doesn't, Fengyun 3 is not there yet, but there is an observation gap. And this is what you see with our constellation. This is really up to date. This is from yesterday, I took it. And you can see the forest 4 to 11, which are operational since March and provide active fire data to customers. And you can also see the really recent satellites, which are forest something until 19, and you can still see that they are in phasing basically, and this is still a commissioning period. So my team and I, we are really responsible for extracting every piece of information we can from every satellite or other source out there. So we have to maintain pipelines for working with 25 plus public satellites, and then our own satellites. And the goal would be to cover roughly every 35 minutes, starting from 2027 with thermal imagery, the entire globe. And for that, we need 80 plus satellites in space. So what's important to us is really 4 key pillars. We want to be complete. We want to not miss fires. We want to be as fast as possible. We want to be reliable and to be trusted. And it's not only enough to tell people, hey, there might be a fire here. We also want to provide the right context. So what was the weather, or what is the weather? How likely this detection is actually a fire or not, or is it a false positive potentially? So why latency is key? So this is a quote from a customer. So they have 60 seconds from the moment they get a notification until they decide whether they send a helicopter with a team to extinguish this fire. This is from a forestry company in South America. Most of our customers, if not all of them, tell us if the data is older than 1 hour, it's not usable to us. It's nice for situational awareness, but it's not really changing how we treat dealing with the fire. And just for context, fast fires in California, they progress as fast as 2 football fields per hour, American football in this case. But we really chase after every minute. So how does this whole thing work? Nothing special, I think. We use both polar and geostationary satellites, and we have 3 main sources. One is the global hubs, AWS, OMETcast, OMETSAT, etc., Geoscience Australia. We have the public directly broadcasted data that we process with CSPP, which is a really crucial part of our system, and with the Chinese processing software we got from CMA. And we have our own Ororatech NRT product. And since we launch CubeSats, we don't really have an option of direct broadcast. This is simply not possible. So we just use a lot of ground stations to reduce latency. In the processing, so of course we run detection algorithms. Most of them are state-of-the-art that were developed by scientists over decades from NOAA and NASA and others. Some of them are own. We also detect burnt areas. A key factor of our process is fire confidence calculation. So we take into consideration things like the fire weather, the conditions, the full fuel moisture, lightning strikes that predated the fire. And the whole idea is to be able to say how likely this prediction is actually a wildfire, or sorry, how likely this detection is actually a wildfire. And some of them we just transform. So we just take data and push it into our system as fast as possible. We aggregate all of them because we want to provide a homogenized product. We save it into our database, and then we push notifications to our customers. And everything is provided either via API, and you can also use our software as a service to visualize the data. So these are the examples that we have with processing direct broadcast dataset from Fengyun 3E, and Fengyun 3F is still work in progress. We have some reliability issues with getting the data and also the algorithm. And the lack of available documentation is really, really a struggle. So we try to find our way and talk to people that know people, whether it's within the PyTroll community or elsewhere. Just a few examples. Yeah, quite a few striping effects in Fengyun 3 that we have to develop algorithms to find these and basically eliminate them. And we suspect it's also related to the monthly updates of the destriping effects they publish by CMA. But at some point before the update, we get these effects and we have to mitigate them. And Fengyun 3 is really a critical instrument for us because of its orbit. So how do we do it with our own satellites? We can't really, of course, do direct broadcasting with CubeSats. And what do is we detect the fires on orbit, we compress the information, and we downlink a few kilobytes of data using multiple ground stations so that we can send alerts as fast as possible. You can see here on the example, so on the right side, there is a fire and how it's detected using VIIRS and how it's detected using our constellation. Right now, we are at the latency of 49 minutes global median. We are aiming at sub 10, but for that, we need more ground stations and we need more satellites. Not surprising, but yeah, we need to get there. So this is on the left, you see our payload, Sapphire, and it was integrated in the picture in the middle. It was integrated in January on board 4 of the Kepler satellites. And the right picture, you see how it looks on our own satellites that were launched later. And it's interesting because the Kepler satellites also have a laser communication link. So basically, it's a constellation of 4 satellites that can communicate one to another. And the orbit is such that one of them is always above a ground station. Sorry. And thus, this way, we can download the data almost instantaneously without any delay. Now, detecting is really not enough, as I said. Sometimes people need to decide if this is a fire or not. And in this case, this was a catastrophic wildfire in the Fraser Island in Australia. And this is how it looked. But when you have a single hotspot, you really need to decide. And for this, we developed fire confidence. And I don't want to go into too many details, but basically, we analyzed the thermal analogy. So we look at the energy, the fire radiative power, we look at the fire behavior indices, and we look at the lightning ignition conditions, and we try to estimate how likely this is actually to be a fire, and then we provide it as part of the signal. And the idea is that our customers, even if we're not always correct, they develop an intuition that they can use to use this metric to decide whether they send a team or not. Validation is key to us. So we really also, in the last year especially, go and chase after every possible reference data set that we can find. And we also encourage our users to classify fires and flag false positives or true positives. So you can see here 2 months of reference data below. And also latency here is also important. And here the US, I think, are really, US and Australia are really key because they publish reference data about wildfires. Every 5 minutes it's updated. And we constantly compare ourselves to this data set and try to improve. Not every thermal anomaly is a wildfire. So what we do is also try to classify as much as possible permanent heat sources such as industry sites, volcanoes, solar panels. These are the main ones, or forest clearings in South America. And you can see here, I think it's 1 month or 1 month of global classifications. And by far, most of them are done automatically, but some of them are also done by users. And the idea is that we don't want to notify people about an industry site in their area. We actually want to notify them only if it's a wildfire. So how does it look? On the left, you see this is our UI, and you see the last 2 days of global wildfires. Everything in black is industry or permanent thermal anomalies. Everything is red is fires. And on the right, you see this is one fire I just picked from Mexico from, I think, a few days back. And you can see how it behaves and how the FRP changes with time. What we also want to do is analyze the post-fire impact analysis. So we detect burnt areas. This is done by using Sentinel-2s and Landsat, so 5 satellites. And now we also added one more algorithm based on Sentinel-3 OCHI. And the idea is we want to analyze how severe the burning was, to also update our fuel maps and estimate the damage. Everything is available via REST API. It's public, you can go there. And I knew this video will not work. Yeah, but if it's possible maybe to click. Yeah, so this was only published, I think, last week, but what you were supposed to see here is a thermal live stream video from one of the Kepler satellites. And it's amazing, you can really SSH to a satellite and see almost a live feed of thermal data. So this was just first light from 1 week ago. Thank you very much.
Thank you, Dima. Very interesting presentation on what Ororatech is up to. Are there any questions for Dima?
Yeah, I have one. Since the early detection is very important, of course, in the case of fires, did you did any comparison with ground detection compared with the system? I don't know if you can say something. I mean, the alert given by someone on the ground with respect to your time in detecting the fire.
Did I understand correctly? And you ask about whether we compare to validation from people on the ground, or
not validation? Understanding how fast is the detection done using your system. Fast with respect to the starting of the fire.
Yes. So where we have the information, we know whether we were faster than. So it's. I'll try to answer. It really depends where. So, for example, in areas where there is a lot of infrastructure and investment, and in, for example, camera state. cameras on towers, we will typically not be the first one to detect a fire. Or if it's very densely populated areas, people will tell about the fire before us, because satellites, they have a glass ceiling. We don't see through thick clouds. So we always compare ourselves to other methods, and we see ourselves also as right now as a very important source of information in remote areas. So north of Canada, Australia, Africa, South America, etc. And when we reach the state when we have 80 satellites and we can actually monitor every 30 minutes, this will improve. But right now, some of the fires we detect first, most of them were not the first.
Any other questions?
Yeah, one question. So for the pre-fire analysis, do you also provide forecast information?
We have our own development of short-term fire hazard. I think it's 10 days into the future. And we benchmark ourselves to the Canadian Fire Weather Index and the Australian Fire Danger Index, I think it's called. So we know we perform better than those, but for those regions. And it's not a global model, so we don't have it everywhere because it's very regional. It depends on knowing very well the fuel types in this area, and this is not something we can just do globally, so we do it area by area.
Okay, if there are other questions for Dima, I encourage you to find him and ask him in person. Thanks again. And so we'll move on to our last presentation for today, and that is from Richard Wright, who is with Dartcom based in the UK. And Richard will speak on the topic of easing the transition from IPOPP, an automation wrapper for CSPP and IMAPP.
Okay, thank you, Liam. Hello, everybody. I'm just going to talk to you today about our experience of moving from IPOPP to CSPP. So first of all, an introduction about the company. We started in 1989, basically making small modules for the amateur market. And then things have progressed from there. We're now a limited company, still based on Dartmoor, which is where the name comes from, in southwest England. Product range over the years has been continuously developed. And over the years, we've produced hardware and software for APT WFACS, MDD PDUS, HRPT, CHRPT, AHRPT, LRIT, HRIT, UHRIT, UMETcast, HIMARIcast, and most recently, X-band EOS reception processing. So that is where we are on a nice MODIS image there showing an algal bloom off Cornwall, where that red dot is right in the middle of Dartmoor. That was received in 2020, our site, and processed with IPOPP. So a little bit about our X-band EOS system. We started developing it in 2012. We use a radome enclosed 1.5 meter antenna. We delivered the first system to the University of Valladolid in Spain in 2014. And we've supplied marine fixed land-based and deployable land-based X and L-band systems to customers worldwide since then. We try and design and manufacture as much as we can in-house, but we do buy some sub-assemblies in, such as demodulators, from manufacturers we've worked with for a long time. So when it came to looking at software solution for the EOS processing, we assessed the options which were needed for processing Terra, Aqua, and NPP. We normally prefer to develop our own software in-house, but due to the complexity of the X-band processing and the scientific algorithms which everybody uses, it was not really practical to do that. So our only two options at the time were IPOPP and CSPP.
We chose IPOPP because it's a complete integrated package which is designed for complete end-to-end processing. It's got automatic ancillary file management, and it's got user-friendly GUI apps for monitoring, control, and diagnostics. It supported all current satellites and has been updated since to do that. We elected to run IPOPP inside a VM on a powerful Windows host PC because this allows easy maintenance and deployment of a tried and tested processing system for our customers. It's also familiar for our existing users of Windows-based software. Most of you are probably familiar with IPOPP, but I've lifted some stuff from the user's guide just to show you what we've been working with and what we tried to replace. So essentially, we have a direct broadcast front end which streams data to RTS TPS, and that outputs files into a landing zone. And then from there, IPOPP collects the files and it processes them according to the configured SPAs and produces all the products into a rolling archive. So yeah, just a text summary of that really. So I've gone too far. So again, this is from the manual. So it's just to summarize that main point there really is the user only needs to configure IPOPP and place the data in the landing zone. So that's it. You don't need to do anything else, which is really why it was so attractive to us in the first place. So in addition to that, it automatically discovers and registers the sensor data, retrieves the ancillaries, registers those ancillaries, schedules the processing, and generates the science products, and it also manages the file system. So that was all good, and we've supplied quite a few systems over the years. It's been pretty reliable, updated as and when DRL released new things. And then the 6th of June 2023, an email hit our inbox, which basically said, this is the end of IPOPP. So I'm sure many of you may have received the same email if you are registered IPOPP users. So this left us with a question. Where do we go next? So we looked at it and said, okay, well, IPOPP supports all the current satellites, so we've got until late 2027 to find a solution. However, it turns out it's November 2026, thanks to the poster out there, being updated by that information. So the suggested replacements were CSPP and IMAPP to cover both the JPSS and MODIS. Problem with those is neither package is automated, the data is not archived, and there are no dashboards for easy monitoring. So it's not a drop-in replacement for IPOPP. So we looked at using PyTroll to glue everything together. Unfortunately, some parts like the runners are not general enough, according to the information on the PyTroll website. And the CSPP runner only appears to run the SDR processing, so it won't generate any level 2 products, so it's not a complete solution. And therefore, it wouldn't enable a drop-in replacement for IPOPP. So then we thought, how hard can it be to make our own wrapper? So we had some key requirements. Those were to watch the output folder of RTS TPS, much like IPOPP does, and then automatically ingest the data sets, move them to a slot in a data archive, along with a record of the current station position, which is important for our marine systems, and a snapshot of the current configuration. So then it needs to automatically start the processing of the data set using either CSPP or IMAPP, depending on the satellite. And finally, it needs to create GeoTIFF versions of the products, which we import into our visualization software. And it needs to automatically manage the data archive, deleting the data sets which have exceeded the configured age. And on top of that, it needs to download the required ancillary files and manage that data cache as well. And for user friendliness, we needed a simple dashboard to show the data sets and the status of the processing modules. So a few moments later, It was actually rather more than a few moments. It was several weeks to get something working. And then we came up with AutoPOP, which is Automatic Polar Orbiter Processor, with a nod to IPOPP there. And it's a collection of bash scripts and associated configuration files. It's designed to allow processing of multiple data sets simultaneously. And the entire processing chain started immediately with, if you've got dependent modules, they will wait until the previous modules have completed before they try and process the data. It's got a simple file-based signaling system, so no complicated messaging daemons hanging around in the background. And each data set can be manually reprocessed if you have an error or you want to try a different configuration. So the configuration files allow adjustment of things like the global settings, of archive size and geotiff projection, and you can enable and configure different CSPP and IMAPP modules and geotiff outputs, which they produce using Polar to Grid. We've got a browser-based Node-RED dashboard, which shows the archive contents, and there's some status icons, and you can also look at the logs for each processing module if there's been an issue with the processing. So the main components of AutoPOP are a daemon with associated scripts for starting, restarting, and stopping it. There is an ancillary manager, which we run as a cron job. There's an archive manager, which we also run as a cron job. And there is a manual reprocessing script, so you can pick a pass from the time slot in the folder name and just tell it to reprocess it, and it will go off and do that. And then there's the web-based dashboard, which we built in Node-RED, which I already mentioned. So the folder structure for AutoPOP is quite simple. You've basically got the AutoPOP scripts themselves, which sit in the user's home folder. There's some symbolic links there to the config, log, and temporary global folders, and they normally live on the data archive share, which is shown on the right there. The actual archive folders themselves, so you've got time-stamped folder name, which is stamped with the time and date which STPS first created the output files. And then in that, it stores the configuration which was used to process the data, and it stores all three levels of data along with the logs and temporary files which were used, which will be kept if the debug option is switched on. So you can check that for clues if you have any processing issues. So the dashboard, which we built in Node-RED, as I mentioned, has got a list of passes on the left there. And then in the middle there, you've got the processing status for each pass, showing you the level 1 and level 2 modules. So a green blob means it's all good and processed. Red cross means it's failed. The little spinny blue icon shows it's in the process of its processing. And the little Zs show that it's waiting on another module to finish processing. And then you can click on each of the processing status lines in the center column there, and it will bring up the log for that particular pass for that processing module. So the configuration files are quite simple. There's a couple of examples here I'll show you. So this is the one for the global config. So you can set your input folder, which would normally be the RTSTPS output folder. There's your data archive there, your global log folder, your global temporary folder. You can globally enable debug mode, set your ancillary maximum age, your archive maximum age, and your Polar to Grid projection, amongst other things. And then another example file here is for the VIIRS level 1 processing. So you can individually enable debug if you've got a problem with that particular module. You can actually completely disable the processing of VIIRS if you wanted to. You can set the number of processor cores, various other parameters there, and then finally you can tell it which products you want to produce with Polar to Grid. There's a load more off the bottom there. The VM, we built a Hyper-V based VM using Ubuntu 24, but you could use other Linux flavors if you liked. We use Ubuntu because we're familiar with it. Our standard PC spec is a high-end AMD Ryzen 9 with very fast disk system. So we're now using PCI Express 5 NVMe SSDs, which will give us more than 12 gigabytes a second read and write, and Windows 11 Professional OS. Onto that, we install RTSTPS, Simulcast, CSPP, and IMAPP in their standard locations. And then we create a Conda environment for each version of each package with the appropriate environment variables and library versions. So some points to note. Some CSPP modules share environment variable names and have different library requirements, hence using Conda. This might not be quite so much of an issue with the recommended Rocky 8 or 9 platform. And some CSPP modules are old and lack support for JPSS2. CSPP and IMAPP produce a different selection of products for IPOPP to IPOPP. And also, it was difficult to work with the original IPOPP folder structure because it works kind of backwards. It's sorted by satellite and then level, and then the products all get dumped within that. So with testing and use, we've been extensively testing and refining it over the past 6 months. It runs reliably 24/7, processing data from all of the Aqua NPP JPSS 1 and 2 on a single PC. We also run our Windows-based visualization software on the same PC. It's much faster than IPOPP, so we can get VIRS level 1, so a typical JPSS 1 pass, which I looked up yesterday. From the pass end, including the polar to grid, we get within 5 minutes, and we can get all level 2, level 1 and level 2 products, including the polar to grid outputs, less than 17 minutes from the pass end, whereas it was taking IPOPP more than 20 minutes just to do the VIRS before. The ancillary downloads are much reduced compared to IPOPP, which is important for some of our customers with reduced bandwidth, such as marine systems. We're gradually deploying this on customer systems now that we're happy with it in-house. And that's an image which shows some interesting fog in the English Channel, which we produced using CSPP. It's a JPSS1 VIRS sharp and true color from the 4th of March this year. And the grid lines have been added by our IDAP visualization software. So where to go next? We will be updating AutoPOP as new versions of CSPP modules are released. We may migrate our legacy FY3 processing chain to AutoPOP. We need to test it with some other Linux distros, including Rocky and Red Hat. And we're currently developing an AutoPOP module for the EPS SG processing software, and it's interesting to see that Polar to Grid will support METOP SG later on this year, so that will be useful for that. And we'd like to gauge wider interest in AutoPOP and potentially make it available to other users if people feel it would fit into their processing chain, if they're an existing IPOP user or otherwise. So just some final words in conclusion. There are many ways to implement a processing chain with CSPP and IMAPP. It's difficult to make a 100% drop-in replacement for IPOP. We've gone for a simple, flexible, modular design for AutoPOP, which is easy to maintain and suitable for other applications. And the VM implementation enables us to easily deploy a black box processor to our customers, and it's easy to update in the future. I'd like to say thank you to Jeremy and Starry at NASA for maintaining the IPOP ancillary server for as long as they have done and sorting out various issues along the way, and the CSPP team for their continuing development support of the package. And that is the end. Any questions?
Well, thanks very much, Richard. Impressive work you've done. And I remember that email on the 6th of June, and I know you were one of the ones who was immediately concerned, and I understand why, but it looks like you've come up with a great solution to move forward. Any questions for Richard?
Got one here.
Alejandro.
Which virtual machine are you using?
So we use Hyper-V, Microsoft Hyper-V, which is built into Windows 10 and 11. We used to use VMware when we started using IPOPP, but it obviously costs money, and we had a lot of issues with it, which took them a long time to sort out. There was a bug involving disk handling, which kept making it crash. So we started looking at other options, and Hyper-V just works, and it's reliable and it integrates well with Windows, as you would expect. Okay.
Any other questions? I've got one. So have you ever, like, late night after a few beers, thought about maybe you should have Linux as your host platform and virtualize the Windows parts?
We have thought of that. But the thing is, so we, as I mentioned, we actually run our processing and visualization software on the same PC, and that's Windows based.
Virtualize it.
Yeah, but why? We're used to, we've always worked with Windows, and we used to, if you get a problem with a dead machine won't boot or something,
okay,
we're much more familiar with fixing that, and you just drop in your your Linux VM to do the rest. There's no reason why you couldn't build, just have a plain PC running AutoPOP, but we just prefer the VM approach, because we can have we got like a development VM, and then we got a production one, which we then update accordingly, and then we just deploy that onto a customer system.
Okay, great. Well, to follow up, I noticed you said, a few weeks later or a few minutes later.
Yep.
It turns out, as far as I can tell, that Gemini and ChatGPT and Claude know quite a bit about DB processing and satellite.
I did ask ChatGPT, and it led me down a garden path.
Really?
Yeah.
So it wasn't productive, or it was productive?
It was not productive at all.
Okay.
It was making all sorts of suggestions about how to do it, but when we actually looked at them, it was either making stuff up, which ChatGPT tends to do, or it was just a really complicated way of doing things. Okay. It was talking about using file watchers and stuff like that to do the, to chain the processing together. Mm-hmm. But we went down the approach of using just semaphore files, basically. So status files, which are much simpler to manage, and it's not another external piece of software which you've then got to install, test, maintain, and everything else.
Okay.
So keep it simple.
Excellent.
That's our approach.
Well, thank you.
Okay. Thanks for inviting me.
So I think we're ready to move on to our community Q&A and technical discussion. So Jess, I'm wondering, did you receive any? Looks like there are some questions.
We did receive some questions. There's also a few questions that came based upon some of the presentations that we just didn't have time for. Would we want to go over those at all, or just ask?
Either and or both.
Maybe let's start with those questions.
Okay.
Well, I guess there's one question for DBNet. So Douglas wanted to know, is Arctic weather satellite being considered for inclusion in DBNet in preparation for EPS Sterna starting in a few years?
Mikael, take a crack at that.
Which satellite? I didn't understand.
Arctic weather satellite.
Oh, of course.
In the short term, and then EPS Sterna in the long term.
Yes, we are looking into this. Of course, AWS is a one-off satellite. It's a development satellite from ESA. So the level of software support, for example, that we expect from CSPP is not quite the same from AWS. There's no operational user support like what we have for CSPP and APP. But we are looking into the possibilities, also in light of the fact that later on will come EPS Sterna, which will be a constellation of identical satellites, identical to AWS. We are looking into it.
So I think that the summary is the answer is yes. The details are to be determined. What do we have next, Jess?
Priyanka, your question from a couple days ago was answered. I'm not sure if you did see it on Slido, but the answer to any plans, this is regarding the talk from Nasu from JMA. Any plans of generating the Leo products using CSP in the cloud? And the reply was, currently there are no plans.
So Priyanka, did you need to clarify, when you say generating the Leo products, who would be doing that?
Can you use your mic?
I always think I'm so loud. Yeah, I was just wondering if users have any interest and in processing in the cloud instead of local, or either ways.
Good question. I haven't heard anybody talk about it in this meeting, but it doesn't mean it's not happening. You know, at SIMS, we've experimented with that a little bit, and it may be that in next 2 to 5 years, we go down that path. And the use case would be as soon as the data are received on the antenna, maybe even in real time, those packets are streamed into AWS, for example, and processed in the AWS cloud. And one advantage for us perhaps would be you don't have to have a processing system at every antenna site. You can have one processing system within the cloud, maybe deployed in different regions, that handles all of your processing. It might be easier to keep it all coordinated and up to date. But I'm sure there's downsides as well. So anybody else thinking about running CSPP or AAPP or the similar software in the cloud?
And I think this might also be related to Graham's question of how can CSPP better serve the needs of users who are interested in processing the cloud? Kind of a tandem question.
Well, maybe it would be illuminating to just get a show of hands from people around the room. 2 questions. First question, how many people have or are currently processing satellite data in the cloud? Okay, so it looks like not all that many. And of the people who raised their hands, does that data come from direct broadcast? Okay, so it looks like just 2 of us in the room raised our hands. You know, at SSEC, I know that the data center has streamed GRB data into the cloud. They stream GRB data into the cloud, and they have users who process it in the cloud. So that's a good example. So, I mean, that question was kind of a plant. We are receiving now science code that's containerized, and that's, you know, coming from the science team. I'm thinking of NGFS. It's targeted for the cloud, to run in the NOAA cloud. And so I think I mentioned in my talk that we're planning with our initial package that we're releasing. It's a joint LEO Geo package for NGFS, that it will be based on containers. And it doesn't mean a user has to know anything about containers. They can still run it just like any other CSPP package, but under the hood, it's going to be a containerized processing chain. And we've been talking about ways, well, if a user really is doing their processing in the cloud, is that somehow better suited to run in the cloud? I'm probably not the right person to answer that question because I'm not doing the work, but we've discussed different ways that we could maybe include some way for a user to configure it to be, you know, to configure like a Helm chart to be integrated to their cloud processing system. So those are kind of along the lines of things we're thinking about.
Any other perspectives on CSPP software in the cloud? Oh, I see Bruce raised his hand in the back.
Cloud is one of those loaded terms that is, you know, kind of effectively meaningless. There's a difference between containerizing science software and running in the cloud. The two are not necessarily codependent in any particular way. CSPP as it is will run just fine in the cloud. There's advantages to additionally containerizing it, but it's not a necessary step for cloud processing. There's ways that you can facilitate running in a cloud environment, by making it easier on like the large ancillary data set sort of stuff can be unwieldy in a cloud environment. But I think it's important to keep in mind that those are related but yet separate things.
Yeah, and you've kind of exposed how quickly I'm out of my depth here because you are definitely one of those people that knows more about this than I do. But it's more than just containerization that I'm talking about. It's if the package comes with, and Levi is also somebody who knows about this because he's worked on NGFS and the CSPP package. If it comes with other things like, Helm charts and it uses Kubernetes and so on, maybe there would be an advantage to a user to having that already, to being able to use what's already in the package.
Well, I can also see a perspective that even if we're not actively doing anything to make CSPP LEO software, for example, run in the cloud, we also won't do anything to make that more difficult or to stand in the way. I can also see publishing examples of here's a recipe for how to deploy CSPP SDR and PolarGrid in the cloud using, I don't know, Lambda might not be the right thing, but using some recipes that someone could go out and actually take action on relatively quickly. But, if you want to check with Gemini or Claude, they might have ideas on doing those things as well. And they might walk you down a good path or a bad path, who knows, but you could try it. Yeah, Bruce.
I just kind of wanted to follow up on what you were saying. I mean, I think that's from a software provider point of view, I would think it would be more important to maintain flexibility in how your software is designed and how it's usable as opposed to necessarily providing a Helm chart. I mean, that's actually narrowing your options and kind of steering somebody towards a solution. It's always better to make the software as flexible as possible, so that if somebody wants to run it in a Helm chart or make their own container of it and run it, whatever way they see fit in a cloud environment. I mean, that's maybe kind of a better perspective to take or a better angle to take in that respect.
Maybe just to finish off that thought, if anyone does want some advice on ways to proceed on installing and running CSPP LEO software in the cloud, we'd be happy to give you some advice and some experience that we've gained. Next topic, Jess. What do we have?
Just following up on the last presentation related question from today, now that Dima's back. There was a question that we just ran out of time, and it was, does the fire confidence filtering allow for real fire to be detected at a solar power plant or industrial facility that normally causes thermal hotspots?
That's a good one.
If we get it right, then we filter this correctly. Sometimes there are errors, but our goal is to, before we send notifications, to have a decision whether this is an industry or a permanent thermal anomaly or not. And we use a bunch of data, whether it's static data or the ones that are updated, I think, every 6 months. And we use global solar array data, and we look at the history of the place beforehand to see if this was already detected and at the times of the detections, and basically try to really consider whether we should send notifications or not. And we track the performance, so we know the fire confidence of the notifications that we have sent and the ones that we have not. And then we use reference data to see and evaluate how well is this predictor performs. And so we have the precision and recall numbers to know how well we are performing, and we're roughly at the 85, 0.85 in precision and 0.9 in recall, which is better than other things, and it's usable. It's not perfect.
Okay, thank you. And if there's any more follow-up questions, please feel free to ask or follow up in Slido.
So Jess, the question that's on screen right now when it says, do you publicly distribute your LEO data products? Was that directed to a particular presenter?
Yes, that was directed to the JMA presentation. So I was, even though the person who asked replied with thank you, I just thought I would share it with the group quick, which was about publicly distributing LEO data products. And the answer was that direct readout data is not distributed to the public, but it is distributed to the DBNet.
Okay, good enough.
And then I can move on to the first question that was put in regarding plans for machine learning implementation in CSPP on advantages and disadvantages.
Geo first, or maybe Leo? How about Geo go first?
I see Levi has a comment.
Yeah.
And Graham, you can jump in and correct me if I say anything wrong. I can only speak for the Geo side. I'm not involved in the Leo side. We already have one machine learning product, Lightning Cast. I'll be giving a talk on it tomorrow. We have another one in the pipeline, Turbulence, which uses machine learning to predict turbulence based on level 1B input. I think from our perspective as the CSPP team, it doesn't matter too much to us whether it's an ML algorithm or not. It's kind of the same job for us. So I wouldn't say there's huge advantages and disadvantages on our side. Obviously, ML on its own has those advantages and disadvantages, but the algorithms come already verified, tested, and vetted to us. Yeah, I haven't even noticed any significant differences in performance between our ML and our non-ML algorithms.
Yeah, I think that was a great answer, Levi. And I'm surprised. I would have thought that the AI ML ones would tend to be faster. And then there's also the form factor. An AI ML algorithm might come with large ancillary data sets. So for some users, that might be important.
So on the CSPP Leo side, there's a few considerations. The first would be the primary source of any geophysical retrieval software that we integrate and release for CSPP Leo is NOAA NESDIS. So if NOAA NESDIS has developed a great ML-based retrieval for some parameter, we'd be very happy to implement it in CSPP. The second consideration is what advantage does it provide for our user community? Because ML is cool and fun and all the kids are doing it, but what advantage does it provide for that DB user out in the field? We always try to keep that in mind because we don't want to release something just for the sake of, well, it's a software update. What does it provide that helps the end user? So there's those two considerations. Following up on Mitch Goldberg's presentation from this morning and the community nature of CSPP, Mitch has developed a quite interesting machine learning retrieval for temperature and moisture profiles. That may be a candidate for inclusion in CSPP. We'll have to see how it goes. We'd want to get our NOAA funding agency and our sponsors in alignment and in agreement, but that's certainly something that would make sense to us. Just on a research level, I'm not saying this would be part of CSPP, but we are putting together right now an ultra low latency CRISP processor that the goal is to identify areas of convective instability very quickly, as soon as possible. And Mitch's algorithm for retrieving temperature and moisture profiles and hence CAPE might be a very good candidate for that application. So I guess the answer for CSPP Leo is it depends. Any other perspectives on someone that knows about a product or a machine learning algorithm they'd love to see implemented in CSPP? One phrase that comes to my mind is optical flow wins. Is there anything coming on the geo side regarding optical flow that might make its way into CSPP Geo?
That might be a Priyanka question.
Priyanka, do you know, is anyone in NESDIS working on an optical flow atmospheric motion vector retrieval for either Geo or Leo?
I don't think I know that.
Sorry, you didn't hear the question, or?
No, I heard the question.
Okay.
Thanks for repeating. I did hear it second time. But I don't think I'm aware.
Okay.
Yeah, I can get information if you said optical flow.
Optical flow, yes.
Okay. Thank you.
If I'm not mistaken, doesn't the NWC PPS have an optical flow retrieval algorithm for winds for polar orbiters? It might. It has some sort of wind retrieval that just between two passes from VIIRS, it will tell you the wind vectors.
Oh yeah, this is AVHR dual wind.
Okay.
For the METOP, for EPSHG, I don't know, but I know that for METOP you had a software called AVHR dual wind. We never implemented it in years. It was a request in the past because METOP A was decommissioned, and in the end we were left with only 2 satellites, and the amount of dual wind we could have got, because you need two pass from 2 satellites, was minimal, so it was abandoned. So
Okay.
it was never carried out with METOP. And then PPS new version, you may have for EPSHG this wind vector that will be now embedded in PPS. But this, I remember hearing about that. So it is a possibility that needs to be checked. Yeah.
So this is a good opportunity to give a mention for the NWC SAF PPS software suite, which actually generates quite interesting suite of products for imagers, including AVHR, tell me if I'm wrong, VIIRS, and at some point in the not too distant future, MedImage.
Yes, and I think they even including now the Mercy.
Yes, and it also supports Mercy from FY3.
Yeah, although we are not doing it yet, but they can do cloud product out of Mercy. Yeah.
Right. Yes, Douglas.
So I just wanted to go back to the optical flow algorithm. I do know that CIRA has a research version called Octane, which I've seen presented in Weather Service talks in recent years. It's been evaluated for...
Is that GEO or LEO?
That's a GEO product using ABI mesoscale sectors.
Okay. All right. Any other topics that we need to address?
Oh yeah, the next one is a suggested topic on management and support of a DBNet station, which Africa RARS will bonify, added value product from stations, resources, mobilization tool. So I think it was just a suggestion for a general topic about management and support of a DB station.
DBNet station. Well, it's not a bad topic. It's probably, there's a good few hours there and a few drinks involved, but you know, it does take a lot of effort to manage and support a DBNet station or a DB station in general. Maybe this is a good time to ask if anybody would like to just, who operates a DB station, what are the biggest challenges that you face today? Is it information from the satellite providers or the software providers or the vendors of your hardware? What are the biggest challenges, and can this group do anything about them? Nick?
I was looking back at the DBNet WMO website.
Yes.
I thought at some point we talked about listing all of the versions, the recommended versions of all the product processing. I don't know whether, and I know we talked about that before, I don't know whether that would be something that would be useful to hold somewhere, but someone would have to update it. But then there doesn't seem to easily be a single place where you could go and look and say, which is the latest version of all of these different processing applications I need on my DBNet station, and how can I easily check now, you know, I'm running the latest versions of all of those. And maybe that's especially someone that gets, like with RARS, and they get delivered a system,
right?
And then there's no one there necessarily maintaining it for them.
I believe NWP SAF does publish on their DBNet web space a guide to which versions of software are recommended. If not, the guide to DBNet, I think, contains some of that information. It doesn't? Really? Okay. Well, let me pick on a use case that's close to CSPP LEO, and that's CSPP SDR. So I'm aware that there are DB station operators out there that still run quite old versions of the SDR software, like version 3.2 or 3.1 or 3.0. And I've got to say that at some point, those things will no longer be supported. Not even that the software won't be available, but the ancillary data that makes those things work, that you need to update every day or every week, just won't be available because we can't keep supporting those versions forever.
And that's exactly the problem that we had when we couldn't run away from the old version of Red Hat that we had, because of we needed the new server and everything, and that took us a while to get away from that. And we were like stuck there without being able to go to the latest versions of some of the software. I don't know whether we had in the DBNet. I think we asked everybody to respond within the DBNet group to say which versions they were running. I don't know whether we can publish that somewhere, or I don't know what.
So you're talking specifically about old versions of software running on newer operating systems? Is that the?
Yeah, but anyone that's running a station, just so that we have some, they can go somewhere for resources to see. Am I running the latest versions, the versions that everyone else is? And B, if they're not, what's the reason? And you know, this question from Ali is how can we help those stations?
Yeah, it's a good topic. I mean, I think, Alejandro, you touched on this when you mentioned CSPP Clavra X, and the fact that, if I remember correctly, that it's a deprecated package right now, but it still can be useful in certain situations. That one was built on CentOS 6, Red Hat 6, which is way beyond end of life. Now, you can run that if you set up a VM or a container that supports that old operating system. But at some point, I mean, do people think that the CSPP team does a good job letting you know, hey, it's time to update? We do this actually for DBNet. We tell the DBNet operators, this new version of SDR is recommended. We hesitate to say required, but we say recommended for all DBNet operators. Would that be helpful information at some point? Maybe, maybe not. So, but back to challenges of operating a DB station. Anybody want to just vent on what makes it difficult to maintain said stations? Jen, go ahead.
We have several orbital antennas. We've had challenges recently with getting upgrades for the EOS Fest, and I want to thank the Wisconsin team for helping manage how to deal with the antenna manufacturer, who historically have been extremely helpful, but lately have been a little bit challenged with turnover in their team. So we're grateful to Wisconsin for that. And then I think the other thing we face is this cloud challenge that you mentioned. We have hardware that's aging and getting to year 4. We have a lot of servers, a lot of VMs, a lot of storage, and we have to think about architecting for the next 5 years as these servers age out. And so I think we have built a cloud-based system. Some very smart software engineers come in and do it. And then you have to balance cost. And, you know, so there's a lot of choices coming up for those of us that might be on the edge of needing to replace hardware and figuring out what to do for the future in terms of how to process so many data, you know, from multiple antennas.
It's a good point. And I don't know if anybody else has noticed, but it seems like server hardware is getting much more expensive.
Very expensive.
In the last 6 or 12 months.
But then, you know, it can be thousands of dollars processing on Amazon, going all the way through the SDRs to level 2, and then the GeoTIFFs, and then that you really run up a bill that way. So you're paying the piper one way or the other.
Right.
Um,
So I just want to mention, if someone doesn't want to say out loud what their question is or their comment, please feel free to put an anonymous entry into Slido, and we won't know who it came from. So even if it's a complaint about the CSPP team, we would like to hear it. Absolutely. So don't hesitate to post an anonymous question or comment. Antoine.
Yeah, so a comment to follow up on CPI, and it's the same experience in EUMETSAT. We wanted to, for example, look at upgrading feed to acquire left hand, because now China is sending satellites that are left hand. And we want, to run business, and we can't even run the business. So we had the same experience here, and I think this community is using a lot of the CPI hardware, and I see a risk here. For example, we've heard that for all the antenna models, the AHP, there are no more spare cards. So if an ACU fails, you basically lose your reception chain. So I see a risk, but I don't see as well an easy solution out of that at the moment, or just waiting for new management to come in with new engineers and they provide solution again. But there is a risk that some of the station basically will lose reception because there is no new hardware to replace, especially the new older antenna model.
Mm-hmm.
And there is not so much we can do at the moment against that. And then the server cost, we have some interesting trade-off in EUMETSAT 2 years ago between centralized processing and the decentralized processing and the cost. And all of EUMETSAT was moving towards central processing on internal clouds. And then there was a trade-off made against the rest, let's say, of what other team would do for the regional processing. And when you laid out a very detailed trade-off, the cost to repatriate raw data was very high. And the other thing is decentralized processing you gain with multiple processing capabilities. So this enhances, your availability. So, but this was a very special case in EUMETSAT that is moving towards centralized processing for maintainability reasons. But in the case of the regional service, it stayed in decentralized bare metal. So you save, actually, you have an upfront cost for your hardware, but once you have it for 10 years. And if what you have to do is do a cost projection for the next 10 years. How much is it going to cost you per processing? And you may end up with a figure that is, you have a high upfront cost, but then over 10 years, it is much cheaper going. So this is a kind of trade-off you have to look at.
I think architecting, I'm not a software engineer, but architecting for the cloud takes a lot of expertise if you're building load balancers and all these types of, if you don't want to keep the instances up in between passes. There's a lot of overhead and smart people required to build a really robust cloud-based system. It's exciting. But,
I think our experience has been that cost is just one of about 10 variables that you have to consider, and you shouldn't assume that it's going to be cheaper. But there might be 9 other reasons why it's better to move into the cloud than buying your own hardware.
And it takes a special expertise for the software engineers to really know how to work in the Amazon environment.
Sure.
I think.
So let's move on to a couple of other topics that we can see. So there was 2 questions from Juan Ping. One of them, I think, expressing a concern about GeoXO data distribution. If it's difficult, if it becomes difficult for a user to receive the full resolution data, it's a challenge for CSPP Geo because it depends on a NOAA algorithm. Maybe it depends on lots of channels. Oh, I like that one. There we go. We can stop right there. I'm not sure what to say about that. Toby did talk about a couple of different strategies that are being considered for GeoXO, data distribution, high rate and medium rate or low rate. I guess we have to see what develops. So stay tuned. Another comment from Wan Ping, which was regarding NEON, about the disaggregated platforms. Multiple sensors on one satellite can produce more precise products. That may be true, but I think my takeaway is the ship has sailed and NEON is going to be disaggregated. But maybe Satya could clarify.
Yes, it is going to be disaggregated. And we are going to have continuity of products for each of the missions. Yeah, that's how it is. Now, we do have, as you all know, a third tier. There are like 3 tiers of products, right? The first is level 1B that goes through GTS, WIS2, yada, 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 buffer, and so on. And there is level 2, which we deemed as on the product list. And there's also a gaggle of level 3 blended products, right? Now, there are some I won't say discrepancies, there are some dependencies. Like, hey, if I have this, then I do that. Like, I need a imager to do a cloud mask, and that needs to be bundled with a sounder to do that thing. We are aware of those things. How we handle it, we need to collectively think about it, right? And I'll also say this, there are 900 products or something like that in our repository that we create at NOAA. And oftentimes when people hear it, it makes their head hurt. So nothing to do with DB, I'm just talking about in general. And there's always an urge and a push to say, who uses these things and can we reduce those things, right? Because it's not just producing, it is archiving, distribution, and things like that. I think we collectively as a science body need to say what are the most important critical things and not put in something into production because there is like a user which uses the product occasionally, right? So it becomes a challenge, especially when you go to this disaggregated architecture because there will be dependencies. Heck, it doesn't have to be disaggregated even in a unique sensor like VIIRS. Sometimes when the sensor on SNPP goes haywire, it will saturate a thermal band, right? Because some lookup table is gummed up. And somebody will say, well, just turn it off. If you turn it off, then 4 other products get affected downstream, right? We saw this thing last year. And we say, okay, you can start turn it off in the ground system. But guess what? Somebody used to call Liam and tell them the ground system is not doing it. And if somebody is processing it in the DB software, it is going to break, right? Because one is a mirror of the other. Yeah.
Okay. Thanks for that perspective, Satya. So there was a question from Alan regarding ocean products for CSPP LEO. In particular, are there plans for CSPP LEO to produce ocean color products? I'll give you my perspective, and then maybe I can ask Lihang and or Satya for their perspective. In the past, the NASA CDAS team has supported a very good cross-platform suite of ocean color products. I'm not sure how it would benefit the community for NOAA. I mean, NOAA has an ocean color product, maybe for VIIRS, but I'm not sure if it's also for MODIS, or how it's different or better than CDAS. Maybe Lihang can comment.
Yeah, that's true. NOAA has an enterprise ocean color algorithm run MODIS and VIIRS called MSL12. The product is being generated operationally. So, I mean, if there's users needs, probably, I mean, it's possible to
made it available to CSPP. But meanwhile, it's already running in operation. It's also, there's a Coast Watch distribute the ocean color product to the ocean user community. So that's another
Okay.
way to find it. Yeah.
I suppose if there were, multiple requests from the CSPP user community to have a NOAA ocean color product, then we would definitely consider it.
Yeah. It's also available on the NOT, the ocean color product from Mears.
Priyanka, did you have a follow-up?
No, I was just going to comment. It is on my list to provide it to you, though. I have ocean color, so
Okay.
yeah.
So maybe it will be coming sooner than we thought. I think there's also a comment from Priyanka about optical flow. So there is a product known as Octane, not in operations yet, but might be transitioned to NOAA operations next year. I'm not sure what DMW means.
Derived motion winds.
Say again?
Derived motion winds.
Oh, okay. Derived motion
So in a
winds.
future version, the science team is planning to include that as well. Is
And
what
this,
I received.
as far as we know, this is a geo product.
Yes.
Okay.
So Priyanka, just so I understand, you're saying that other than Octane, there's a possibility that a future update to the current GOES derived motion winds algorithm might use optical flow?
That's why I understand from that sentence. I just got that much. I don't have much further background information.
Okay, yeah, that's really interesting.
Yeah, Jamie Daniels' team is planning, so I'm assuming that he will include it in DMW.
All right, last call for comments or topics. Okay, well, let's wrap it up for today. Thanks, everyone, for sticking with us, and we'll do it again tomorrow starting at 9 a.m. Have a good evening.